Hello, and thank you for joining us for day 2 of our Integrated Distribution Systems and Planning training. We are joined today by Lisa Schwartz. My name is Carrie Worthington, and Lisa Schwartz and I are co-moderating today. We are just getting started, and thank you all for joining. I see our numbers increasing. Thanks. We want to remind you that we have evaluations that we take very seriously, and we would really appreciate if you would take a moment to fill out day 1 of the evaluation. We are posting it again into the chat box for you all. And we will get to that in a moment, but we will send you the link to the evaluation from day 1 and the slides for today. They are found on the Lawrence Berkeley National Lab website. And all of the PDFs are there with the agenda and all the bios for our speakers today. So I'm going to turn it over to Lisa to guide you through the agenda.
Hi, welcome back. So we're going to build on the sessions yesterday, and our focus today is on the integrated distribution system planning processes. We're going to kick it off here with Paul Martini with a short session on the integrated distribution system planning components. And then we'll do a deeper dive into several emerging distribution planning analyses having to do with forecasting loads with increasing levels of distributed resources, hosting capacity and interconnection, and non-wires alternatives analysis and locational net benefits. And we'll also get into pricing programs and procurement analyses for distributed energy resources. And after our break, we'll come back and Paul will be back to talk about how do you incorporate resilience into distribution planning. And then we'll cover grid modernization and planning. And at the end of that segment, we'll have a segment on investment economics, really important to public utility commissions in particular. And then we're going to end the day with ways that states, particularly public utility commissions, are engaging in distribution system planning. So let's get started right away. Paul?
Thank you. So as Lisa said, we'll be talking here in a brief presentation on the components of the distribution system planning as it's evolved and emerging around the country. Next slide, please. But as a starting point, it's helpful to understand what's the scope of distribution planning and sort of thinking about that most broadly. We're going to, obviously, as Lisa said, we're going to focus on particular aspects throughout the day, but from a broad standpoint, distribution planning encompasses really 3 primary dimensions that try to address customer needs. The first, reliability and resilience, which we'll go into a little deeper in a later session. Distributed energy resource integration and utilization, and safety and operational efficiency, which has classically always been done, as well as meeting incremental customer load additions. So these 3 domains are sort of at the heart of the distribution planning that we are increasingly thinking about, and the need to be thinking about how to integrate the relationship between the analysis that's done for each of these different areas, which have their own different sort of aspects to them, and then how do they converge into a proposed set of investments over a time horizon. Next slide, please. So one of the things that has been discussed in the industry for some time really is looking at where we needed to evolve the distribution system to meet changing customer needs, particularly as related to distributed resource integration. More recently, I would say, particularly over the last 5 years or so, with increasing severity of weather events and implications on storms and the need for resiliency, we've started to see that become much more into the fore. Certainly with respect to looking at grid investments, but this kind of transition from stage 1, which, on this S-curve that some may be familiar, that I developed many years ago, and into stage 2, where there's much more customer, increasingly more microgrids, and distributed resources, that's kind of where we've been for the last 5 to, in some cases, 10 years. As we look ahead to 2030 and beyond, as longer-term distribution planning is starting to do, we need to start to think about where we may be heading with distributed energy resources, particularly in light of, say, FERC Order 2222, and what may come after that, what we might develop with respect to community or multi-user microgrids that have resources that are, in front of the meter as well as maybe behind the meter, as alternative rate designs to NEM that allow for energy export, start to change the nature of how this system operates. All these factors come into a different kind of distribution system and have interrelated impacts on the various planning domains that I had mentioned previously. So next slide, please. This slide that I'm showing here starts to give some sense of what are the dimensions that we need to think about in an integrated planning process from a longer horizon, over the next 10 or longer years, as may be the case in terms of thinking about a long-term planning horizon that is typically now being incorporated in an integrated distribution plan. I won't go through this in detail, but just to give you a sense of the kind of changes that are underway, some of these we've talked about in the industry for some time, but these are now becoming reality. And then where we're heading in the tomorrow dimension is one that's going to, as I said, going to have some additional implications on how we think about planning. And that really leads to the next slide, where we need to think a little bit more broadly about the range of inputs into the planning process now for distribution than maybe we had previously. So as part of the broader integrated or comprehensive system planning discussions that have been underway for a couple of years, or very specific state level activities at looking at integrating resource planning with and transmission with distribution, that clearly, as identified there in the blue inputs, is a dimension that comes into play. We've been talking about, we'll talk more later today about how resiliency feeds in. But the other piece that's important to incorporate is also what's happening at the local community level related to local city, county, even town level or neighborhood level sustainability and resiliency objectives that have been increasingly developed that factor into the distribution system in a pretty important way. So understanding those inputs is increasingly something that needs to be considered. Next slide, please. I think we wanted to do a quick poll here at this point. So the question, what level of integrated planning is needed in your jurisdiction over the next 5 years, and perhaps even a little further, but over the next 5 years? And here, question sort of builds in terms of the level of integration that you're thinking you may need. Okay, good. So next slide, please. Thank you. So the integrated distribution system planning process is represented in this graphic. There's a fair amount of detail here. Some of you may be familiar with this diagram that originated with the work that I did for the Minnesota Commission about almost 4 or 5 years ago now, and looking at how the various elements have come together. There's a couple of areas here that we'll want to highlight in the color shading. The first is the planning inputs and objectives, which is represented by the green. That really gets to what I was talking about on the prior slide. The yellow is the first level decomposition of the various analyses that are undertaken. And I'll highlight a few aspects. Granular locational forecasts The current system assessment, it's really important to understand what your starting point is for any planning process. That's what that box represents. The resilience and reliability analyses I'll talk about in a later session today. Those combine into thinking about system analysis. So as we think about the power flow analysis, we think about voltage and quality and other service quality dimensions. That's where the system analysis really comes into play. And then that informs then what the near term, generally the next up to 2-year cycle for planning, and then the longer term distribution planning, they'll generally be 5 to 10 years, and in some cases now even looking out to 15 years. So that's really how that block sets up. The interfaces in the orange are related to things like the broader system forecast as opposed to then what's done at a more granular level. The resource and transmission planning is simplified there, and that just represented in that box. Obviously, much more set of interfaces and interactions. Those then, building off of the system analysis, feed into how to think about alternative options for various grid needs that have been identified out of that system analysis. And then those tie into the overall annual plans that distribution plans that feed into operational planning for the next year's activities, as well as longer term integrated distribution system plans, and then how that then ties also to a grid modernization strategy and any implementation plans. So in summary, these are the various elements that make up an integrated distribution system plan. I'll note that today, in many cases, some of the analysis that I was talking about in terms of asset planning, which isn't called out explicitly here, but is part of the system assessment, and then what asset planning is required, that tends to be a group within a utility that is doing that at a medium-sized to larger-sized utility. There'll be a separate group looking at asset planning. There's generally a group and an analysis separate that's looking at resilience and reliability that will also tie to the asset, but those tend to be two different sets of activities. And then the area where you're looking at DER integration and thinking about those dimensions as relates to things like hosting capacity analysis, but then also what upgrades on the system may be required over time, and the complexity, managing the more sophisticated technology that would need to help that. That tends to be another group that looks at that. So part of this integration is not just integrating the various analyses, it's also an effort to integrate the various work practices within the utility, and in some cases the regulatory proceedings that are informing those activities, as well as the outputs of those analyses that then are being considered potentially in separate proceedings as well. So thinking this holistically and the implication on integration is one of the more significant challenges with this kind of effort. Next slide, please. So we're going to go into this a little further, but this pie chart gives an example. This isn't precise, but it gives a rough sense of the cost allocation, or budget allocation, I should say, of how capital is deployed within a utility. Again, this is somewhat representative of the kind of allocation that happens. The shading, which I'll go into further later today, illustrates the degree of which the budget is impacting reliability and resilience. So the investments that are made, this is representing capital, the investments made in these categories, the blue wedges, essentially have an impact either directly or somewhat supportive of achieving a certain level of resilience and reliability. So as we start to think more about resilience as part of the planning process, it's really important to understand the relationship to these other budget components and how they feed into it, and understanding how the planning processes that tie to each of these wedges, and as I just mentioned, there are different parts of the planning process that ties to those particular wedges, how those really need to sync up and really be optimized to achieve whatever the objectives are, and around resilience, reliability, and the other dimensions that are that we spoke about at the outset in terms of those three domains. Next slide, please. So the other thing that to point out is that as we think about investments in the grid, there is this hierarchy, this sort of Maslow's hierarchy of investment, and it really builds on a solid foundation of the physical infrastructure, starting with safety and electric, code compliance, the resilient and reliable distribution structural design. So thinking differently about the architecture of the grid to ensure that you've got a good base structure, obviously addressing any aging infrastructure that needs to be replaced. And on top of that, then start to overlay the intelligence, if you will, sort of the distribution automation, both sort of the basic kinds of automation that have been around for 20, 30, in some cases 40 years, and then overlaying more sophisticated, sensing, protection, and control schemes on top of that, and integrating those other components in the basic automation. And then, thinking about, structural changes and how we can utilize utility community partnership kind of microgrids. So how do these microgrids come into play? These are ones that would involve more of the grid side as part of this mix of thinking about what the structure of the grid ought to look like to achieve certain resilience. And then as well, how do we incorporate customer microgrids into this mix to understand how do we achieve overall resiliency objectives and other considerations, renewable targets and customer choice objectives as well. Next slide, please. So in summary, there's basically a set of considerations here with distribution, integrated system distribution planning. One is that we've got a multi-objective planning set of requirements. And as I mentioned, they often involve or will derive significantly different uses of the distribution system than we've traditionally had. We've always talked about for the last decade about two-way flows. Well, that's definitely the case, and certainly over the next planning horizon for long-term plans over the next 10 to 15 years, we're going to see much more of that. And of course, depending on location, but generally speaking, I think we're going to see more of that. And so there's a need to think about how the planning process needs to address that, on top of the fact that we have greater needs around resilience that need to be taken into account with the system. So one of the first things is, what are the appropriate planning objectives and criteria for your grid of 2030? So starting to look ahead and really getting a sense of where are customers heading, where are the state policies, where are other activities driving towards in terms of need for the grid to serve. So what are those objectives and criteria? There's clearly a sense of uncertainty about what the pace and scope of the change that needs to be addressed. So it's not certain that everything's going to happen as we think they might. And certainly you don't want to be making investments, too far off, either too far ahead or behind those needs. And so understanding how to think about the uncertainty of that pace and scope as it relates to then thinking about incorporating some flexibility in the planning and investment strategies is an important dimension. What is the appropriate investment prioritization model? There's various ways that folks have been thinking about this. We'll talk a little bit more later today about it. What is the level of collaboration that's required to achieve those objectives with resilient, safe grid? As I mentioned, one of the things that people are starting to recognize is there needs to be more engagement at the community level to understand what's changing from the local communities in terms of where they're heading and how that then needs to feed into the distribution planning, because that's directly connected. What level of oversight and transparency is required? Certainly, we've spent a lot of time over the last decade increasing transparency in the planning processes, but there's more to be done, I think, in understanding what that looks like and how to refine based on lessons learned to achieve the overall buy-in, both from customers and stakeholders. I think I have some references to share on the next slide. There's a new volume of the DSPX guidebook that I worked with Joe Palladino on over the last couple of years, plus many others that are participating actually in these sessions. The distribution planning work that Lisa and Juliet Homer had put together with some colleagues. The Minnesota PUC IDP docket is a good reference for those that aren't aware. And then if you're thinking about how these things tie together, a practical example is the HECO Integrated Grid Planning report that talks about how they're looking at integrating the various resource transmission and distribution planning together, that if you hadn't seen that. So there's some links there. So I'll stop there. I guess I don't know if there's another poll or Q&A.
Thanks so much, Paul. That was great. We do have questions coming in from the audience, so thank you so much for those. Just really quickly, you touched on this a bit, but how can PUCs include local planning on utility distribution plans? This is in part about jurisdictional boundaries and what PUCs can consider. Thanks.
Yeah. So I think that so the kind of planning what I'm talking about, sort of local community, isn't the community doing its own thing in terms of its own distribution planning, but rather that the communities need to be part of that engagement and discussion, because as we've seen, cities and counties have been increasingly putting their own sustainability plans together. They've been putting their own, and as part of that, electrification has increasingly been part of the mix. They have their own resiliency plans, identifying critical facilities, other infrastructure they think is essential to meeting their resiliency objectives. They may have identified vulnerable communities. Those dimensions, which at a state level and a commission may have identified those categories, but how that plays out specifically at the distribution system and in particular areas, and then how to think about prioritizing investments across communities is an area that I think could be explored. So it's really incorporating the communities as a key stakeholder in the planning process. And most places I've been involved in around the country, they're not really at the table having that part of that conversation as part of the stakeholder group. And I think there's an opportunity there, particularly as we see where we're heading over the next 10 years.
Thank you for that. The next question goes back to a question that was raised yesterday with Mr. Patrick Dalton from ICF. I'm not sure if you're on the call, but he said that utilities would not approve certified inverters for DER interconnections with intentional island mode on. Presumably, this is because additional review and time is needed to determine how to reintegrate when the grid comes back online. Is there work being done to simplify this review so certification would be sufficient, or will we need more in-depth reviews of these projects? Thank you.
Yeah. So I think just to clarify, I mean, I caught part of Patrick's presentation, but not all of it, and I'm not sure I caught that part. But what he's getting at is the IEEE standard, in the way that it's being implemented in most interconnections, it doesn't allow for islanding. So if the circuit goes dead and that's at the point of interface at the meter, after 5 seconds, then it opens up. I mean, that's according to the standard. He was referring in part of the presentation to grid forming or grid following inverter modes, and you then need to change modes to be able to allow it to stay connected, or if you're talking about allowing that resource to stay connected and export energy into the grid. So there's some work that has to be done to allow that to happen, both on the technology side as well as then making sure you're not backfeeding into the distribution circuit so that you're creating a problem. If we're talking about being able to then have the breaker open with the grid interface and then be able to supply customer load behind the meter, that can be addressed, and there are solutions for that, and that has nothing to do with the interconnection. So I think that depending on what we're referring to here, I think there's potentially some answers. Certainly in the case of community microgrids that have front of the meter resources or resources behind the meter exporting into it, there are resolutions to some of those based on some of the early projects of that type. But I mean, there could be a follow-up if there's an interest.
Thank you. So the other question I have, and please keep sending in your questions if you do have them. Can you please say more about best practices for addressing grid modernization strategies and distribution system planning?
How to incorporate this grid modernization within the distribution planning process? Is that the question? Yeah, we're going to actually go into that in quite a bit of detail later today. But generally speaking, grid modernization comes out of that system analysis and looking at what the needs are and understanding your current system assessment that I showed on, I think it's slide 6. And so if we think about that those grid needs, or what we're calling grid needs coming out of that system analysis, then helps you understand incrementally what you need to accomplish from an engineering standpoint. Then from that, you then translate that into what are the sorts of investments you need to make that, to achieve that capability or the functionality that you need, and then what technologies then derive to that. But I'm going to go into much more detail about that this afternoon in relation to the grid modernization planning.
Okay, great. Well, we have just 1 minute left with you. Do you have any final comments or anything you'd like to reinforce?
I think the main thing is having is the issue related to setting clear objectives, and to the extent that you can turn those into planning criteria in terms of what it is that the plan needs to address, and over what time horizon. The other thing is that a lot of questions that we've gotten through the technical assistance program with commissions is about trying to understand what sort of flexibility may be available within the planning in investments. So I think that's another dimension that could be explored as more and more states are starting to incorporate scenario planning into the distribution analysis. Those should be used as a basis to think about the optionality to understand milestones or signposts that then give you a sense of the pace and scale of what change may be needed. And then how do you tie your investment strategy to those, I think is an important consideration. I believe Michigan is already pursuing that angle. And I think that's something others may want to take a look at.
Terrific. That's great. That's great advice, and will help folks prioritize. So let's give a virtual round of applause to Mr. Martini, and we will move on, and I will pass the mic over to Lisa. Thanks.
Thanks, Carrie. Thanks so much, Paul. We'll hear quite a bit more from Paul later today, and I'll get more into, like you said, the grid modernization aspects, as well as resilience and grid and integrated distribution resilience planning. So let's welcome our next panel. It's a 1-hour panel. It's going to be terrific. We've got Ben Sigrin first from National Renewable Energy Lab talking about forecasting loads with distributed resources. Then we have Patrick Dalton back to talk about both hosting capacity and interconnection. And then we'll wrap with Debra Lew, who'll talk about locational net benefits, non-wires analysis, and sourcing distributed resources through programs, procurements, and pricing. So first up to bat is Ben, and following the presentation, I'll moderate Q&A. Please send your questions in at any time. And at the end of this presentation, we'll have a 15-minute break. So welcome, Ben.
Thank you, Lisa. Just confirm you can hear me. Okay, great. Thank you, everyone, for taking the time out of your day. So my name is Ben Sigrin. I'm a research engineer at NREL. I'd like to also thank Patrick and Debbie for joining the panel. My research at NREL focuses on forecasting customer-driven adoption of DERs, looking at how we can better model that, how we can better model consumer decision-making and the behavioral drivers of decision-making. So that culminates in a tool that we've developed at NREL called the DGen model, which I'll talk about later, and I'm happy to make a big announcement about today. Next slide, please. One more. I should also say portions of this presentation were developed by Andrew Mills at Lawrence Berkeley National Lab. So when we think about why DERs matter in load forecasts. There are several aspects here that are important. So first, as we're developing load forecasts, we're thinking about how we can make investments in the distribution system, better replace aging infrastructure, and planning for what the needs of the future will be. These DERs can help as part of procuring capacity and energy to meet peak demand and meet energy served. They can also be used as proactive investments to increase hosting capacity of the grid, which Patrick will talk about later. And then, of course, DERs can also be weighed against other policy objectives, other perhaps decarbonization goals, and so on. So it's all part of the mixture of trying to understand what are the costs and benefits of having customer-driven DER technologies. Next slide, please.
Hey, Ben, this is Lisa. We have a poll to queue up, I believe.
Okay. All right. So this is a poll, so please let us know what you think is the right answer here.
And you want to provide the right answer?
Oh, yes, sorry. My bad. Okay, so thank you, everyone. So the, sorry, I'm trying to find my notes. I don't recall. Okay, so the correct answer is actually B. The correct answer is that through 2019, approximately 15.8 gigawatts of DC rated had been adopted in the United States through 2019. So people were close. Okay. So this is a schematic here. You may have seen similar concepts earlier in the training that trying to understand the impact of distributed solar that can have on transition distribution infrastructure investments. So, the magenta line is what the peak load on the distribution system feeder would have been, the blue line without PV generation, and then what is the net load with PV generation. And so that can either defer when the feeder's peak capacity has been reached, or of course there are other circumstances where, for example, the deferment is never reached if there's continuing energy efficiency investments or other changes to load patterns. Next slide. So this was another study that Lawrence Berkeley and NREL did, trying to quantify the impact or the value of increased accuracy in long-term forecasting. So this was run via a combination of capacity expansion and production cost modeling to see what would be the cost of either systematically over or under forecasting customer-driven distributed solar adoption. And so, of course, if you over forecast distributed solar adoption, then that means that less has actually been adopted than you planned for, and you will need to procure generation and capacity in some other way, which can be difficult to do and expensive. And if you under forecast DPV adoption, then of course it's the inverse, that more has been deployed and you've sort of overbuilt the grid, and that's an unnecessary expense to the ratepayer if that comes to pass. So the costs of misforecasting distributed DER adoption can be quite high. They can range in the order of millions of dollars per terawatt hours of sales. And of course, that's ultimately dependent on the level of penetration and the time period considered. Next slide. So another challenge in forecasting loads with DERs is trying to get at the differences between net load versus what some people call raw load. So raw load would be, actual load would be the amount of load on the grid that's actually consumed prior to the distributed solar generation or other DER generation. But what we actually usually observe at the nodal level is net load net of the DPV generation. So when we're developing load forecasts, we should be aware of that. There are regions of the country, cities, states, ISOs that have enough distributed solar adopted where it's a non-negligible correction to make. And so that's a methodological challenge, but you know, there's a case study here about how PJM adjusted their net load and raw load forecasts. Historical assessments to develop a better load forecast. Next slide, please. So I think that many people in IRPs and DRPs are forecasting distributed solar, customer-driven distributed solar adoption. Of course, there are many other DERs that are starting to be adopted widely: electric vehicles, energy efficiency measures, price-responsive appliances, etc. So I think that we have to think about these other technologies as well in developing long-term planning studies. Also thinking about not all DERs are behind the meter; some can be front of the meter. And so we outline a method that one can use to forecast distributed solar adoption, and I would posit that it can also be used to forecast adoption of these other technologies. In some cases, there are other types of DER systems. Combined heat and power is one that comes to mind, that are very specific to an end user, that are known to be of a large size. And in these cases, it might be the case that more of a local knowledge approach that the specific distribution planner might be aware of large investments that are coming online versus sort of the invisible customer-driven adoption. Next slide. So I'm happy to announce that this week, NREL open sourced its primary tool, which is called the DGen model, that is used to forecast and develop scenarios of future customer adoption of DER technologies. So if you have a GitHub account, please feel free to navigate to our site and browse the code and start using it. So this is part of a larger process for NREL, where we are participating with all 7 ISO RTOs to use this tool to develop joint forecasts, but also to build sort of staff capacity at the ISO level and their member level to use these tools and to improve the planning process. So for more information, please check out our website. And I would say that for anyone on the call that is trying to develop DER adoption forecasts, we're looking for additional partners for this study. We are funded at the moment, so we'd be happy to work with you to help you out to get started using the tool, or to point you to resources that already exist. Next slide, please. So this is an example of the forecast that we developed jointly with MISO staff. Please note that this is a pending publication. It is not considered a final result. But so essentially, we used the DGen model, and working with MISO staff, adjusted the inputs, adjusted the different parameters to better align with the long-term planning assumptions that MISO uses as compared to other ISOs or NREL generically. And we're also working on not just transferring the model code, but also transferring the data, and thinking about how can we set up a permanent database for MISO so that MISO or their participants can use it as a resource going forward. So we want to work with you. Please email me if you're interested in learning more. Next slide, please. So here, I think, are some of the informed questions that commissioners can ask about forecasting. So I apologize, because this is normally a 1-hour talk, so I've condensed it to 10 minutes. But just thinking about for people that are developing forecasts, what are the primary factors that drive the forecast of adoption? Does it consider economics only? Are there other factors that are influencing the forecast outcome? How do these forecasts tend to account for an observed phenomena that new technologies follow an S-shaped curve of adoption, that initial adoption is quite limited, and then there's an acceleration period followed by sort of an asymptotic saturation? Thinking about, are there other sources that you could compare forecasts to? There are, at this point, several third parties that develop forecasts, either publicly or through licensed reports. And then thinking about, to what degree is the forecast driven by top-down methodology versus bottoms-up, and how do you connect these forecasts to either at the consumer level or at the feeder level? Next slide, please. So that's it for me. Thank you for the whirlwind opportunity, and here are some resources to get you started if you have some more questions about this state of the literature. Thank you so much.
Thanks, Ben. We'll next hear from Patrick Dalton from ICF talking about hosting capacity and interconnection. Thanks, Patrick.
Thank you, Lisa, and thanks, Ben, for that presentation. That was great. Again, my name is Patrick Dalton. I'm with ICF. Happy to be back here to talk about hosting capacity and interconnection. So kind of starting just with the takeaways right off the bat. Similar to what Paul was saying about grid mod, hosting capacity objectives are a very important starting point to ensure that the result is actually usable in a way that stakeholders are expecting it to be used to achieve those benefits. So we'll talk a little bit about objectives. We'll talk about a few of the different fundamental methodologies that are available. There's really three main methodologies that are in use across the country, and they have some trade-offs that we'll look at. And then finally, want to look at some of the different methods across the country in terms of granularity and system information that's presented, because it does differ quite dramatically from region to region. Next slide, please. So starting with just the basic, what is hosting capacity? It's essentially the amount of DER that can be accommodated on a circuit with existing conditions. So the existing equipment, the existing load, and the existing generation that's already been interconnected, while maintaining safety, reliability, power quality, sort of the core objectives to utilities. It's typically presented in a map form to the right, but the underlying data is also useful for some of the use cases. Next slide, please. And just briefly, where does hosting capacity fit within integrated distribution planning? It can be used to inform interconnection studies. That's one of the use cases that we'll look at, but it can also be used for sort of longer term distribution planning, looking at where upgrades might be needed based on DER adoption, or informing locational value, which Debbie is going to talk about a little later. Next slide, please. And so looking at three of the most common use cases and thinking about the importance of really spelling out the objectives and the use case prior to embarking on a hosting capacity effort. The first use case, the most common one today, is informational maps for developers, so outward facing maps from the utilities that can help guide DER to locations that can accommodate the resources without upgrades. The next is automated screening. So the hosting capacity results could either be used through a manual process for engineers to streamline the screening process for interconnection, but also it could be used in, in an automated fashion to really streamline interconnection, to minimize the manual labor that's really needed to review interconnection applications. And then finally, as a distribution planning tool, and this is probably the least developed use case, informing locational value is something that's being done in some jurisdictions, but the broader tie-in with distribution planning and hosting capacity is still really being worked out. Next slide, please. So looking at how some of the different jurisdictions that have adopted hosting capacity, and this is a non-exhaustive list, but mapping some of these use cases, it's pretty apparent that the outward-facing maps for developers is really the primary use case. And other jurisdictions have started to look at the technical screening use case and the distribution planning tool use case, but those are earlier in the progression. Next slide, please. And now looking at a specific example in New York of how stakeholders are currently applying hosting capacity maps, I think it's somewhat intuitive that the highest value for stakeholders, or the highest use case, is just simply what remaining hosting capacity is on the system. But beyond that, hosting capacity maps can start to provide information about whether there might be upgrades, kind of more costly upgrades. 3V0 is an example here. It's a specific substation protection type of technology that can be quite costly. And so hosting capacity maps can also furnish that type of information if an upgrade has already been performed at a substation, or if a developer might face that upgrade with their project. Next slide, please. So now kind of zooming in on this interconnection use case and thinking of hosting capacity as a tool to streamline interconnections, there's really kind of two places that it can tie in. One is in this pre-application phase of providing developers with that information up front that we were talking about. It can supplement or even supplant the process of pre-application data, where a developer approaches a utility with a specific location and asks for relevant interconnection information for that location. But it can also be introduced later on in the process during what's marked the supplemental review here, which is an engineering analysis to look at voltage thermal protection limits. We're going to do a very fast overview of what those limits are in a few slides here. Next slide, please. I mentioned that there are three main types of hosting capacity analysis. They go by different names, but streamlined, iterative, and stochastic is one framing of these. The streamlined is a method that's EPRI drive tool is probably the most prominent example of this method, and it uses simplified algorithms, kind of simplified calculations, and not a full power flow methodology. And so it's not quite as accurate as the iterative method, which actually is performing the type of full-blown power flow study for every location on the system, very similar to a study a planner would perform during an actual interconnection study process. It's iterative is more computationally intensive, so it can take more time to run the scenarios, which becomes more of an issue with very frequent updates over an entire system is where you may start to reach some of those limitations. And then stochastic is a third method that sort of randomly places DER at different locations on the system in order to come up with a range of different hosting capacity values. And this has been incorporated in some commercial software and by some utilities, but I tend to think that streamlined and iterative are bubbling to the top. But as we'll see here on the next slide, there's, oh, excuse me, this isn't the next slide, it's actually a little bit later, but anyways, next slide.
Patrick, why don't we break in here for the poll?
Okay, yeah, that sounds great. Okay, so the question is about how your state is using hosting capacity analysis currently. So is it not currently available yet, or are there maps, or are there some of these more advanced use cases? All right, thank you for your responses. So the majority of respondents said that hosting capacity is not currently available in your state. So I think that I'll maybe reemphasize the point again about how important objectives are prior to really embarking on a hosting capacity analysis and really clarifying what those are. So I guess hopping back back into the presentation here, I just want to flag how data integrity is really a persistent challenge for hosting capacity. This is similar to like a ADMS adoption or other systems that really rely on the system data being available and accurate. But as we think about the more advanced use cases of actually approving interconnection applications based on an automated method that maybe doesn't have somebody looking over the data in the analysis, this data integrity issue becomes even more prominent. And there is an example of Southern California Edison actually developing an automated process for improving their accuracy and accounting for system changes, because the distribution system is very dynamic and changes all the time based on storms or upgrades or a number of other factors. Next slide, please. So now we're going to do just a very quick overview, next slide, please, of the different types of technical criteria that hosting capacity is looking at. So we're going to quick fly over each of these bullet points, covering voltage, protection, thermal, and reliability considerations. Next slide, please. So this chart may look familiar if you happen to sit on my presentation from yesterday, but reverse power flow from DER can create high voltage, and there are set limits that equipment can tolerate. And so an important evaluation during hosting capacity is just what is the steady state voltage going to be after DER. Next slide, please. Another voltage related issue is looking for the voltage change from a DER unit being on to a DER unit being off. It's called voltage fluctuation sometimes, and there are a couple components, but the one that is most relevant here is a rapid voltage change limit, that if there's an abrupt change in the output, and there are a number of factors that can cause that, not so much like cloud cover, something that's an even faster event, there can be a step change in voltage, and that can cause equipment problems. Next slide, please. Thinking of capacity constraints, thermal limits are really driving capacity constraints, the amount of power that can be pushed across a conductor. And where a limit may be reached in hosting capacity is where the level of reverse power flow starts to encroach upon the equipment rating limits. So this is another key criteria for hosting capacity. Next slide, please. Kind of on the unintentional islanding slide, and the question came up of, are inverters capable of forming islands or other generation on the last presentation. When inverters are in grid connected mode, or any DER for that matter, it's important from a safety and power quality perspective to assure that DER won't energize a part of the line that's disconnected from the system unless it's intentionally designed to do so in like a community microgrid or multi-user microgrid approach. So flagging the potential for load and generation to be matched where an island could occur is another threshold that's commonly applied. Next slide, please. Kind of continuing down the protection side of things. I might be having a lag on my side. Thank you. There's this concept of relays being desensitized. So the inability of the utilities relay to detect an issue on the system is kind of this desensitization issue. And when DER feeds a fault, so if there's a tree that falls on the line and both the utility system and the DER are feeding that fault, that can lead to this desensitization phenomena. And it's really important for a safety and reliability, from safety and reliability perspectives, that utility relays can detect faults on the system and quickly isolate the problem. So if DER is added and it prevents that ability, that's an issue, and that's something that hosting capacity is screening for. Next slide, please. On the operational side, some hosting capacity methods, and this is maybe in the minority currently, but some are looking at this operational flexibility. So if the system needs to be switched around, and we looked at an example on my presentation yesterday where there's an issue with one of the substations and now DER is served from a different feeder or a different substation. If we don't plan to be able to accommodate that DER in the alternative configuration, then it may be forced to go offline because it's causing some sort of voltage or thermal issue. So including a margin for operational flexibility is a feature of some hosting capacity analyses. Next slide, please. And then finally, in terms of the kind of technical impacts, there's the potential for constant changes of DER output based on cloud cover for solar or changes for wind, causing fluctuations in output. And if there's equipment nearby that's intended to respond to changes in voltages, these output fluctuations can cause this equipment to operate very frequently. And that's what we're looking at on the right-hand side is this study that was performed by NREL looking at how many times a piece of equipment would need to change taps. You know, this is voltage regulation equipment, mechanically actually switches contacts, mechanical, metal contacts. And so there can be wear and tear that we need to watch out for. And so that's a common threshold for hosting capacity as well. Next slide, please. Next again. So we're going to very briefly cover some of the features that hosting capacity maps or analyses may include. And we can just go right to the next slide, a summary of some of the features and the methods. I'll include this mostly as reference to look back on, but I do want to flag on the left-hand side the analysis methods, the 3 different methods that we discussed. And there's more in the streamlined and iterative columns, a few in the stochastic, and then in terms of some of the features, we'll look at these in detail, but it does vary from map to map or analysis to analysis. Next slide, please. There's been a trend towards including pop-up information on hosting capacity maps. So instead of just having a color-coded map that shows the potential hosting capacity, actually including some of that pre-application data that I mentioned as well in a pop-up window. Next slide, please. We'll actually skip this one as well, but if you want to look back in terms of what pop-up information is useful, there's a slide on that. Another feature that's becoming increasingly common is specifically calling out PV hosting capacity versus other types of DER. And what this is doing is really just taking into account when PV is producing and the load at that time. And with PV being a very prominent type of DER, this can be useful. Next slide, please. EVs and load more generally is a feature that's starting to pop up more and more in hosting capacity maps across the country. So this is an example of a national grid map, but Pacific Gas and Electric also has load hosting capacity. A number of others do as well. So as we're thinking about beneficial electrification, this may be an important feature to ask for as well. Next slide, please. Wanted to briefly show that there is a range of granularity in different hosting capacity maps, kind of starting on the left-hand side, blocks that show kind of regionally what the hosting capacity might be. In the middle is sort of more of a heat map where the lines are blurred. And then all the way to the right-hand side is sort of actually showing the feeder lines. And there can be privacy concerns potentially with, different levels, but it's good to know what kind of granularity you're aiming for as well when embarking on this. Next slide, please. I'll just very briefly mention that locational value is a feature in very few maps currently, but could become increasingly important. And Debbie's going to talk more about how locational value can be used. Next slide, please. And then sort of an advanced feature as well is actually allowing users to download load curves or even just all of the hosting capacity results for a location. And this is an example from Southern California Edison. Next slide, please. And very briefly, just want to talk about some of the limitations of hosting capacity data. We talked about that. As you get further up in the system, kind of substation transmission level constraints aren't always accounted for. Downtown networks are very specific design. It can be challenging to account for those in hosting capacity. At the other side of the spectrum from substation transformers, as you get very close to the customer, there can be data challenges with that information as well. And so that's not always available. And then employing smart inverter functions and settings as mitigations to understand, if smart inverters are used, what the hosting capacity could be is another challenge that's being addressed. Next slide, please. I think in the interest of time, I won't read these questions to you, but they were sort of sprinkled throughout the presentation. So a couple things to think about as you're considering hosting capacity. And the next slide is resources for more information. And thank you for the time. I know that was a bit of a quick flyover, but I appreciate the opportunity to speak with you today, and I will pass it over to Debbie now.
Thanks, Patrick. Can you guys hear me okay?
Yes, you sound good.
Yes.
Great, thank you. So I apologize in advance. I had some emergency dental work done this morning, and I'm gonna try really hard not to bite my tongue while I'm talking. But I'm gonna talk about locational net benefits, DER compensation, DER implementation. If you go to the next slide, as you can imagine, there is no one size fits all answer. That's because DER are so many different things, right? They can be generators, storage, demand response, energy efficiency. And also there is a difference between the value the DERs provide and the avoided cost to the utility and the compensation that they earn. And then finally, compensation depends on how it's implemented. Are you going to issue an RFP and choose the least cost, or are you setting a price and looking for organic uptake, or are you trying to incentivize something? And then finally, because DERs can provide a specific service at a specific time in a specific location, the evaluation can get really granular, and this can be cumbersome. It can also raise equity issues. Should I be treated differently from my neighbor because of where we are on the feeder? It can also get at the heart of really unlocking the value of DERs, though. Now, there's different ways to pay for DERs. Net metering is the most common, but you could also set a tariff for what you'll pay. And that could be based on the value of DER, or you could have a feed-in tariff based on avoided cost. Because net generation or net consumption is often a basis for compensation, and because some DERs are load modifiers, rate design becomes really important. And then finally, non-wires alternatives, they're different. These are alternatives to traditional T&D upgrades. And utilities issue RFPs for non-wire alternatives, and then they select the least cost solution that's going to meet their needs. And compensation there is based on the offers that are received. But in order to determine which projects they should go out to bid for, the utility uses locational net benefits analysis. And that's what Patrick just showed on those maps. And the locational net benefit analysis is essentially the avoided cost of the traditional utility solution. And they use that to help them prioritize projects. So I'm going to talk about procurement, pricing, and programs, and it's going to be a little bit fast here. So let's go to the next slide.
And Debbie, we're going to queue up a poll here.
Oh, okay, sure. So we just wanted to try and get a sense of what folks were doing in terms of deploying DERs in their regions. And everything. That's great. Okay. So we're going to start talking about non-wires alternatives. So these are hot right now. Wood Mackenzie recently issued a report showing about 850 megawatts of non-wires alternatives that have been identified or implemented in the US. But implementation has been slow, and non-wires alternatives are not yet, a really big market share for DER providers. Projects are only moving forward about 40% of the time. It used to be that energy efficiency was a big non-wire alternative. Now it's battery storage. Tends to be front of the meter. Ben just talked about front of the meter, so not netted out from generation behind the meter, but rather its own metered resource. FERC Order 841, which allows storage as small as 100 kilowatts to access wholesale markets, is probably going to encourage more storage solutions in non-wires alternatives because you'll get more value stacking. In addition, costs are dropping. So why aren't more projects moving forward? Some of the big reasons given is that they're more expensive than traditional upgrades, or they're less reliable than traditional upgrades. If you go to the next slide, we're seeing non-wires alternatives mostly being identified through the big processes, through the New York REV process, the California DRP process. In some cases, like in Vermont, the utility is required to prepare a long-range transmission plan updated every 3 years, get enough time to identify and implement cost-effective non-wire alternatives. Obviously, a utility that's under cost of service regulation is going to be incentivized to spend more money on infrastructure. So there's also new innovations coming out, like Central Hudson Gas and Electric. They split the savings in non-wire alternatives so that 70% of the savings accrue to customers and 30% of the utility. And that helps incentivize the utility to actually do non-wires alternatives as opposed to the traditional solution. You go to the next slide, I'm going to dive in deeply to California and their distribution investment deferral framework, because it's a really nice framework for how one might think about setting up a process. So first, the IOUs establish their historical peak demand, and they forecast their load and their DERs. They do all the stuff that Ben talked about. And they disaggregate all this down to each substation feeder. So a study for each of these feeders to ensure that the system can operate under normal conditions, under abnormal conditions. And if they have a problem, they identify, where's the need, what kind of need is it, is it a capacity problem, a voltage problem, when does it kick in, what hours does it happen? And then they develop their own utility-owned traditional projects to fix these needs. Now you start with the cheapest things, like maximizing use of existing equipment or modifying the circuitry. And then you build up to more expensive things like a new distribution circuit, or really expensive things like a new substation. And then they screen these projects, and they look at things like timing. Is there enough time to do a solicitation? That can take 3 years to go through that whole process. Can DERs help with this problem? And what you can see here on the right, the top shows 262 grid needs that SoCal Edison identified in their process that they issued in 2020. And then the middle right shows that when they screened that for timing technical screens, they got down to 14. And then at the bottom, this shows their prioritization of these 14 projects. So they use 3 metrics: cost effectiveness, where they use this locational net benefit calculation, which again is the avoided cost to the utility of the traditional solution. And so sometimes the traditional solution, that would be a really cost-effective potential project, and that would be rated green on this metric. And you can see that in the first column here. And then forecast certainty is the second metric. So do they really need it? Do they know they need it? Do they have SCADA measurements to justify this? That would give them green in the second column. And then market assessment. Does the current DER market fit the problem? You know, is it a 4-hour need or is it a 12-hour need? Is it something that's predictable or unpredictable? You know, if it's 4 hours and it's predictable, you know, that would get you a green on the far right column here. And you can see they rated their 14 projects. The top 2 tiers that are all yellow and green for these metrics are the ones that SoCal Edison decided to go forward with in this example. So if you go to the next slide just shows that there's a number of different behind the meter or in front of the meter aggregations and technologies that they're interested in, and also that they're thinking ahead to wildfire mitigation and behind the meter solutions that can provide resiliency with other things going on in California right now. And if you go to the next slide, this shows an example the Eisenhower project. So the blue is the crosslay circuit coming out of the Eisenhower substation. And I realize it's hard to see, but the bottom right table shows in red that starting in 2022, they're going to start to be overloaded on that circuit. They're going to run out of capacity, and the hours of the need are 5 o'clock, 6 o'clock, 7 o'clock, and they're going to need a maximum of 2.5 megawatts and 4.4 megawatt hours for that particular need. So this gives you an example of what this looks like. You go to the next slide. I wanted to explain a little bit of this process that they just went through. So SoCal Edison filed their grid needs assessment and their distribution deferral opportunities with those 6 projects that were proposed for doing an RFP. They filed that in August 2019. CPUC approved that in December, and SoCal Edison launched the RFP in January. So, you know, that took a little bit of time right there on its own. And at the end of their peak season, they run through another distribution planning cycle, and they found, as they ran through this next cycle of planning, that things had changed a lot. So the 6 projects that are shown on the 2 right tables here changed a lot. And you can see from the 2019 column and the 2020 column, 2 of the projects are no longer even needed. Pachanga and Alessandro, the 2 in the middle. And the other 4 had drastic changes. And in particular, that one that I just showed you, Eisenhower, on the bottom left of this table, you can see that the need went from 2.5 megawatts to 16.2 megawatts. Now, the traditional upgrade cost is still the same, but what the DER providers need to do on their side in terms of what kinds of capacity installation they need to put together, it needs to be much bigger now. And unfortunately, because this was so late in the game that this happened, the bidders were given a week to revise their bids. And so this was a little bit of a unhappy situation for folks. And it's just an example of some of the challenges that can occur in the procurement process. And so obviously there's things that maybe we need to do to try to align some of the planning cycles better with some of the bidding cycles. It also just points to the fact that these things are moving targets, and there are a lot of changes going on in the system. Okay, so now if we go to the next 2 slides, I want to talk quickly about pricing. Various ways to think about how to set tariffs. For example, some places like Hawaiian Electric used to have feed-in tariffs for different technologies because they wanted to encourage uptake of different technologies. New York is working on value of DER. Austin has long had a value of solar tariff. What do these calculations look like? So here's an example on the right of a value of rooftop solar calculation. And it's showing a stacked value for different solar penetrations for municipal utility. And for each of these, example, distribution losses, you could run a distribution power flow and calculate losses on sample feeders. For energy and transmission losses, you could run production cost modeling and transmission load flow analysis to calculate those. You could run a loss of load probability analysis to calculate avoided capacity. And then there's a lot of other additional attributes, steel price risk, avoided RECs, emissions. So there's a lot of potential weeds that you can get into, and a lot of opportunities for conflict in these kinds of calculations as well. If you go to the next slide, one of the things I wanted to point out in this particular example is that this particular utility, in addition to evaluating a value of solar tariff, they wanted to look at different rate designs because they wanted to close that gap between the cost of servicing their PV customers and the revenue that they received from those customers. One of the things we looked at for them was time of use rates and how they acted like storage on the system and provided a lot of savings just on their own. And this is just looking at time of use rates and how much value they would bring to the system in terms of capacity and energy compared to what this low scenario here is 13 megawatts of PV. So it provided a similar kind of value to the system just in setting the right prices to begin with. And if you go to the next slide, as you all know, DERs are much more than just rooftop solar, right? There's lots of DER technologies that can shave load, shimmy, shift load, and this is really the low-hanging fruit. But in order to get at this power, you've got to have strong price signals and enabling technology. And that's what this graphic is showing. This is the summary of hundreds of experiments done in dynamic pricing, looking at the impact of having a high peak to off-peak price ratio and enabling technology, which is shown in the lighter blue dots. So providing both of these things can get at a much stronger impact. And then if you go to the next slide, I won't dwell on this, but ERCOT is a really good example of how very strong pricing, how demand response, and how their 4CP program, which is basically a coincident peak cost allocation process, really helped them to meet peak load with a really tight, less than 9% capacity reserve margin. So if you skip over 2 slides, we're going to talk quickly about programs. So one of the programs I wanted to mention was Holy Cross Energy. This is a really small distribution co-op. They don't have a lot of staff or a lot of resources, and they've really tailored what they do for the biggest bang for the buck. So they focus on electric vehicle programs where they essentially trade you a level 2 charger for the opportunity to control your electric vehicle charging. They also have a peak time rebate program where they pay you up to $1 per kilowatt hour for critical peak periods. And they're working on a distributed battery program currently. And I'll also say for their peak time rebate program, there's no penalty for non-performance. there's only an upside for customers. And I just say this because it's in contrast to what we see in demand response programs where, you'll tell customers you're going to call on them 100 hours in the year, you get to the 20th hour of the year and they start getting upset. Or in contrast to a program where they may be financially penalized for non-compliance. This is a really nice, everyone likes this program. Okay, now if you switch to the next slide, I wanted to talk also about a large utility, so Arizona Public Service, who is a leader in pricing and programs. So they realize DERs, electrification, if we don't control this can exacerbate grid issues. But if we can control these, either directly or through pricing, this can fix or alleviate grid issues. So what APS did was they partnered with Energy Hub. Energy Hub provides the DERMS, so that management system for all the DERs, and they're customer facing, they do the communications and control. And APS thought about they have a bunch of different programs. I want to focus in on just the first two here. They thought about, should it be bring your own device? How should we replace out water heaters? It turned out they had a couple specific feeders with issues they wanted to address. And so they targeted two programs to those specific feeders. And instead of waiting for organic turnover of the appliance, they said, we're just going to give you essentially a free water heater in exchange for control of it. And with storage, the utility gives the customer a $500 credit. They own, they maintain, they control the storage. But if there's an outage on that system, the customer can use that battery for backup. If you go to the next slide, then APS sort of brings all this together, and it's really critical to think about the situation that your utility is in. APS is in a situation where they're right next to California, right next to high levels of solar. They got high levels of solar themselves. 1 out of 4 days last year, they could buy negative price energy in the regional market. They're looking at their existing programs, eliminating those programs that are exacerbating their duck curve, and instead focusing more on programs that are helping them with peak and flattening the load shapes. And I just wanted to show what they're doing there with that camel-shaped curve. They basically have really strong time of use rates. So there's a peak ratio of 7:1. Time of use ends, the off-peak ends at 3 p.m. And they wait until after the peak rates hit a little bit. And then they put in their 2-hour demand response to help kind of flatten that out a little bit more. And that helps them kind of orchestrate their load profile. It's a little crude, but it's still very effective. And the next slide is basically just some questions that you might want to ask your states about procurement. And the slide after that is just resources for more information. Thank you very much.
Thanks, Debbie. That was terrific, as always. We have several questions that have come in. I'm going to start, Debbie, with you, a question that came in. This has always been something that commissions and utilities struggle with. How should the customer's longevity be evaluated for non-wires alternatives? For example, if you've got a large industrial customer that's proposing a combined heat and power project, and the energy would be valuable, at the right time, but that entity could be at risk of ceasing operations or changing its operations. So, you're comparing that to a traditional utility solution like a transformer or a conductor that maybe, would not have these risks. How does the utility and regulator assess these kinds of risks?
That's a really good point. So I think there's a lot of those risks in terms of just trying to get customer uptake, customers moving, customers not liking their DER or not really being able to use it properly or to its full potential. I think that there is that potential. And I think this is still something we're trying to work through. Like I say, you can have non-compliance contracts with some of your larger customers, and then you can also put yourself into a position where, people get pretty upset at the situations that they get locked into financially. So this is still an active thing that's trying to be worked out as to how we manage with customer change over time. It's a really good point. There's some risk that either the aggregator is taking or the customer is taking, or the utility, somebody's got to be taking that.
And those risks are something that the utility reviews as part of the non-wires alternatives process, right? And that goes into some of the, I said at the very beginning, some of the reasons things aren't going forward. You know, the utility might feel that the solutions aren't as reliable as what the utility solution would be. So there's some of that, and it would depend on sort of what the actual need is. You could imagine that if there were needs that were, you know, very unpredictable, that could be a lot more risky for the utility to want to take on. Let's go to Patrick with a couple questions that we've received. One is about risk, so I'll start with that, a different kind of risk. With high levels of DERs in some states, distributed energy resources, is there a risk that the distribution system would cause issues for the transmission system? And since you're sitting in Minnesota, right, are you aware of issues in MISO that you might be able to give some examples, and how utilities and MISO are working together on solutions?
Yeah, that's a great question. And there certainly is a threshold where DER could be pushing power back onto the transmission system, and transmission power flow studies need to be done. It's typically first done at the utility level, and if the utility flags that this is potentially a planning issue, then that could be bubbled up to MISO and included in their studies. So there are certainly interactions between transmission and distribution. And I think another aspect of that, beyond just the reverse power flow, is understanding what DER is out there, and if an event occurs, if there's a disturbance on the system and a large amount of DER could trip offline, that could start to cause reliability issues, sort of system stability issues. And we haven't really approached that point from what I've seen in Minnesota yet, but there are studies out there in California that show that there are sort of these DER mass tripping events that we need to start thinking about what that reliability impact is. Some of that is being addressed by the IEEE 1547 standard when compliant equipment becomes available in, maybe a little over a year or so, that these will just be standard features to try to protect bulk system reliability. But yeah, understanding, what load is hidden from the DER, and those dynamic responses, and kind of just the normal thermal power flow types of issues are going to be increasingly important. And I can't necessarily speak to what thresholds have been reached in MISO, but my sense is that we're pretty early on in the Midwest in terms of DER impacting transmission systems.
Right, and there are those provisions that you just mentioned in the new standard for ride-through that, are being addressed by some utilities already. And some of that equipment does have the smart inverters that you talked about yesterday, that capability built in. So let's quickly go to one last question before the break. Patrick, this is still with Patrick. Are there any examples where the hosting capacity analysis models that have been used a part of interconnection studies or project approvals? So I think, you could talk about, for example, California would be one place.
Yeah, absolutely. The models are increasingly being incorporated into interconnection studies, and California, like you mentioned, is an example of that. It's a good use case for maybe certain size units that you don't need to do custom settings on, There is sort of this issue of optimizing DER integration that if you can configure them with specific smart inverter settings, that can allow more hosting capacity for the next unit. So that's one of the challenges that I mentioned with like smart inverter settings and incorporating it in hosting capacity, that if we just sort of say, yes, the system can accommodate it, go in with whatever settings you'd like, that may limit future interconnections. So it can be done today, and it's being done for certain sized units, but the kind of optimizing and really maximizing hosting capacity can still be a challenge to fully automate for all sizes of DER.
Thanks, Patrick. So I think we are out of time here. I think we could talk with these presenters for a long time. I want to thank Ben, Patrick, and Debbie. Terrific presentations. So we're on a 15-minute break, so we'll be back at 15 minutes past the hour. Thanks.
Welcome back, everyone. Thank you for staying on. We are getting started on our second half of the second day. We have Mr. Martini back for round 3. He is very eager to share all of his experience working with utilities along the way over the years and in different regions. So please take this opportunity to ask any questions that you might have, and we will hope that your questions will get addressed. So without further ado, I'm introducing Mr. Martini. Thank you.
Thanks, Carrie. So building on the discussion we started earlier today on integrated distribution planning, here we're going to zoom in on one of the dimensions we discussed on resilience planning. Next slide, please. So as I was illustrating earlier, there are really 3 sort of domains of planning analysis that happen. And the one we're going to focus on here is on reliability and resilience. Next slide, please. So one of the things as we think about resilience and planning for resilience is really thinking, pretty broadly about the role that electricity plays in our modern society, not only individual customers, but also those critical facilities and essential facilities within a community as well. So this interrelationship to other critical infrastructures or essential services like banking or gas stations or the like, as may be identified within your state, within the communities within your state. It's important to understand that context and the relationship to the electric grid and the dependencies, the requirements that those infrastructures have with respect to electricity. That is, do they have backup solutions or not? What are the requirements that they have for both experiencing no outages to, if there is an outage, what's the implication for their ability to get back up and running? And what's the impact then on that community? So this understanding of the interdependencies is an important consideration going into any resiliency analysis. And this touches on part of the reason I mentioned earlier about the need to engage with local communities, because this is where this information really starts to emerge, in addition to what may come out of the state state emergency services efforts will also be another source of good information to feed into this process. Next slide, please. So as I described,
I think we have a poll. Do we have a poll for?
Oh yeah, thank you.
That's off. Yep. Launching it.
So the quick poll, what is the level of maturity of threat and risk-based assessments for distribution resilience planning in your state? And again, this kind of builds. So the first level is kind of focused on asset hardening and vegetation management and reliability assessments. What are the classic kinds of things that utilities may have done? The second is to more systematically build on that and add environmental and cyber threat assessments. So environmental meaning, storm severity and the like, and the impacts of those, as well as increasing potential for cyber threats. Additionally, that starting to look at something around applying those things into a threat risk-based mitigation analysis, for example, a bow tie type analysis. And then sort of fourth is those things plus starting to apply some form of a risk spend efficiency analysis to prioritize investments to be able to address the overall objectives. Or you're not clear on what utilities are doing right now. Okay, interesting. Okay, so what we're going to do is cover each of these dimensions a bit, and certainly we can explore further in the Q&A. So if we could go to slide 5. Oh, sorry, yeah, slide 4, thank you. I forgot where we were. Thanks, Gary. So as we had talked about earlier, coming back to this flow diagram of integrated distribution planning, what we're going to talk about over the next few slides is really zeroing in on a couple of dimensions related to the planning objectives and criteria, and then the resilience and reliability analysis that I've highlighted here in the red boxes. We'll also talk about how that then informs and we think about developing longer-term plans in terms of prioritization and identifying solutions. So we'll cover a number of these dimensions, but the next couple of slides are going to zero in on these first couple. Next slide, please. So one of the things that in any sort of planning and then how it relates to implementation and then ultimately operations is there is this overall life cycle where we start with planning and objectives or objectives and criteria, the integrated planning process, identifying solutions, solution prioritization. You know, the diagram that was shown on the prior slide really is a decomposition of these 4 dimensions that are represented here. But as we think about resiliency and reliability planning, it's important to understand the operational stage and then how this ties to a post-event evaluation and then the link back, the feedback loop back into the objectives and criteria. So there's this sort of life cycle, if you will, of how this planning fits into the overall life cycle, as I mentioned. One of the things is important to understand is there's a lot of definitions and discussion in the industry around definition of resilience versus reliability. For the purpose of this discussion today, we're going to talk about resilience in the context of an engineering context, that is an architectural context, which is the grid's ability to withstand an impact from cyber and physical threats. So the ability to not fail, to not have an outage is what we're referring to in terms of resilience. Sometimes it's talked about, I've heard some vendors talk about resilience in terms of recovery in the operations mode, but that isn't really correct from an engineering or architectural standpoint. It's really about withstanding the threat in the first place. So in this context, we're going to use it in this definition. So the next slide, please. So when we think about what it is we need to be resilient against, what are we going to need to be able to withstand? We need to be able to assess those potential threats, those things that might otherwise break the electric grid, if you will, or cause failures on different components of the grid, a circuit breaker, transformer, pole, wire, etc. What are those things? This is an example coming out of Hawaii that was done by Hawaiian Electric as part of a broader engagement with local community and state emergency services and other folks to look at, and obviously the commission, to look at and assess what are the various threats that they may see on their system and start to understand in terms of priority in relation to the potential impact on the electric system and by extension then customer impact, critical facilities, societal impact. And so this idea of going through and identifying those potential threats, and you can see that cyber attack is one of those. It may be a little difficult, but it's the 4th one down. So you've got hurricane, tsunami, flooding, cyber attack, and so on. Each area obviously is going to have its own unique set of issues. Hawaii doesn't deal with ice storms, and obviously in the upper mid-continent, it's a particular challenge. And so each area has its own unique set of threats, and you would want to do a prioritization of those so you can start to then understand the impacts. The next slide, please. Now, as part of that process, you're also trying to understand that each each type of event is going to have its own level of intensity with respect to the impact on this electric grid and therefore customers, critical facilities, vulnerable communities, and the like. And so there's a different scale related to different events. You can have what we call a reliability event, which is a very short duration outage. Let's say a car pole accident. Somebody runs into a telephone pole and knocks it over, and there's an outage. Or a squirrel gets into a distribution across a distribution insulator and it causes the line to trip, and then you have a very localized outage for a relatively few number of customers in short duration. We call those reliability events, and typically account for those in our metrics as a reliability event, the SAIDI-KD kind of metrics. Those things that are considered major events are what I'm trying to represent here in the blue shaded boxes. And those start to have different dimensions. Those start to be either a major event, but at a local scale, meaning that it's in a fairly confined area, say within a county, and the number of customers and so on, and the impact is more localized. We can have something I would consider a major local event that starts to cut across multiple counties, let's say, and starts to have a much larger impact. Certainly, some of the major storms that we've seen have had, certainly started out at the major local event, and a major regional event is where we start to cross, state lines, and now we have let's say a weather event that basically cuts across multiple state lines, and so you have a larger regional impact that may be involved. The reason for thinking about this is twofold. One is, what's the scale at which you need to think about the level of resilience? The other is, what's the level of coordination that would be needed to be able to think about planning for that kind of event, and certainly in terms of responding to such an event. That also comes into play here. But it's really important to understand how to think about these and really unpack the threats as they may be, have different scales, and understand what that means in terms of potential grid failures. Next slide, please. So one of the methods that is kind of a best practice in a number of industry sectors, by the way, but is being applied in the electric industry, is something called a bow tie assessment or bow tie analysis. And this is a way to think about what are the potential threats that have gone through the prior analysis, and understanding both the nature of that, either weather related or natural disaster, say an earthquake or the like type event, and or a cyber threat, and understanding those threats, the potential impact to the system, and which is the second step on the left, identifying physical and cyber vulnerabilities. That's the potential impact. Then identifying what are those potential solutions that might prevent that specific failure. So hardening, so when we think about distribution hardening, that's an attempt to basically prevent a specific failure. In that case, maybe wires going down or the like, or pole snapping. So there are specific solutions identified to that vulnerability. That vulnerability is the specific failure that you're trying to avoid, which is in the middle of this bow tie diagram. So whether it's a substation transformer or a transformer out on a distribution line or a pole or a conductor, any of those things would be these specific failures. Now, in every case, we're not always able to avoid having that particular failure. And so what you want to have is plan B. That is, what happens if that failure still occurs? Do you have a mitigation in place to basically reduce the impact, both on the physical grid as well as customer impact in terms of outages? So, so the potential impacts are that next step. If your first option, that is to try and prevent the failure, is, so what are those potential mitigations? You try to or the need, and then what are those potential mitigations, solutions, and then what is the resulting net impact that may occur as this, if there was a failure, and you use your mitigations, because typically you're not able to mitigate every potential failure that may occur. So what's the result, and is there acceptable risk tolerance related to that, and as well the cost associated both with the plan A, that is to prevent the failure, and plan B to mitigate that potential failure. So it's really important to kind of think about this in this sort of plan A, plan B type analysis to think about it. Now, one of the things that occurs, as you can imagine, is that a number of these different threats, and environmental threats in particular, have some overlapping sort of impacts on the distribution system. So, they're not necessarily going to uniquely impact the distribution system differently in terms of the kind of failures that may be created, and the kinds of solutions that may be employed may be able to mitigate multiple types of threats. So part of this analysis is also synthesizing those potential impacts to understand how a potential solution may be able to address multiple threats. Next slide, please. So as we talked about earlier, most of the capital investments in the distribution system have something directly tied to enabling greater resilience and reliability, or as I'm showing here with information technology and customer service requests, have a they're not so directly, but there's still aspects of that what's done there that can address reliability and resilience if thought about as part of the process. So it's very important that we really understand what it is we're trying to accomplish with resilience and reliability, because a lot of money that's being spent in the distribution system has this potential for making things better. And so being able to make sure as part of the planning process that we have line of sight to how that's being thought about, not only just in grid modernization or in those categories called resiliency and reliability, but also when we think about aging infrastructure replacement. So in aging infrastructure replacement, are we, when we're replacing that infrastructure, are we taking into account what is a better design practice for hardening or for how we configure the system, such that what goes in isn't exactly what came out in terms of design, but rather is an enhanced version that takes into account reliability and resilience. The emergency repairs is actually storm damage repair. And so, the last thing we want to do is put exactly out what was, failed, just so that it can fail again at some future date, but rather, what you use for the emergency repairs is the improved kind of approach or improved equipment, such that you take advantage of that opportunity that presents itself when you have to replace that damaged equipment by putting the newer design-based equipment out. What this means, by the way, in practice is that the design standards and the related equipment associated with that design standard that's more resilient is sitting in inventory, so that when crews go to get the equipment to go make the storm repairs, they're bringing their new design-based equipment, not the old sort of types of equipment that were used under the prior less resilient designs. So it means that there's more effort on the front end that needs to be done so these things can actually happen in practice. There are additional benefits by thinking about this resilience that then accrue to other aspects of that Venn diagram I talked about at the outset for planning, which has to do with things like DER and microgrid integration, how we think about other needs that we have as we move more into electrified societies, particularly with electric vehicles and the like. And so there's overlays and interrelationships there as well that should be taken into account. Next slide, please. So as I touched on earlier, it's really important to understand that there is this Maslow's hierarchy of investments, really starting with the base infrastructure. So what are we looking at with the fundamental poles and wires and that infrastructure, the conductor, whether it's underground or overhead? What's our basic capability what does that look like in terms of its condition, its current status and capabilities, and then how do we think about the overlay of more intelligence on top of that to achieve the outcomes that we're looking at. As I touched on the prior slide in the text but didn't speak to it, one of the things that's increasingly important is having visibility into the state of the grid. Certainly as in those places that have adopted smart metering have realized that understanding whether customers are, have power out and additional sensors on the distribution to be able to understand where faults are detected really help understand the response time in terms of restoration, but also as we think forward in the planning through the evaluation, how we might think about hardening in particular areas to be able to, or other dimensions that we may do to mitigate the impacts of various resilience threats to ensure power continues to be available for customers in critical facilities. Which leads to then thinking about what are some of the options we might think about to structurally to enhance the resilience of the grid, and that's where microgrids really fit in as an option to the fundamental architecture or structure of the grid. It's another dimension of how we might ensure continued operation of the system, particularly when we have an event. So it's another tool in the toolbox to think about as we look at this overall stack. But it's important to recognize that microgrids, to really work effectively, need to have these other dimensions as well. You can't just have a microgrid and the rest of this not to work to really make these things effective. And part of the reason is that microgrids, by design generally, are not operating in island mode, but a very few hours out of any particular year. 99.99% of the time, microgrids are interconnected to the grid, and in many cases, those microgrids have resources that are participating in wholesale markets or providing services to the grid or the like, and the economics are really dependent on that, which means that you need to have an ability to have that that interconnection, robust interconnection. So there's a balance there in terms of thinking about the relationship about how microgrids can play in the broader grid as a whole. That's an important consideration. Next slide, please. So one of the things that, building on that, is that we started to discuss as part of some of the activities with the Department of Energy is around thinking about how to consider the role that grid investments and microgrid, or what we'll call, even backup generation, what are calling point solutions. So community-based solutions versus point solutions being for a specific customer or a specific facility, for community meaning multiple customers, multiple, maybe a whole community. So how do we think about the balance of that to achieve our overall objective? I developed this 2x2 as a way to start to conceptually think about the relationship on the resilience solution scope side, those point solutions and those community-based solutions. And not to say these are either or, the point is that there's a portfolio of these that are needed. The societal benefit, where is the benefit that that accrues to these various solutions? Is it an individual customer that may have their backup battery or backup generation? Is it a single critical facility, but that facility serves a community? And so therefore there's a greater societal benefit. Is it a set of solutions that address all critical facilities or all critical facilities and essential services, which gets to a certain level of societal benefit? And then community-based can address those critical facilities and essential facilities, but also a wider range of residential and business communities, say an industrial park or residential community, and then entire neighborhoods, town, or all customers in a particular area, say a county or the like. So this can scale as we think about this, but one of the things that we haven't really been in a number of places yet that I'm aware of, really been looking holistically in the planning process about what's happening on the customer side and how do we take that into account when we think about resilience set of solutions and portfolio. Now, this isn't to say that these customer actions need to be part of some non-wires alternative. I'm not saying that at all, because customers are doing these, and many of us, I'm sure, in this conversation today, have already been taking their own individual actions. I certainly have, with what I've been going through here in California. So it's really a question of how do we think about what the need is and understanding what the current state is with respect to what solutions that individual customers or communities have taken, and what is the role that the grid needs to do to both enable that, as well as be able to understand its role in terms of enabling a broader resilient infrastructure. So this is a challenge. I don't know that there's an immediate answer. I know there's some colleagues at some of the national labs that are working on some of these opportunities. Bobby Jeffers at Sandia in particular has been working with a number of communities to try and work through some of these portfolio analysis. But this is an area, I think, as we start to look at the distribution planning process, is something that would be a useful exercise to discuss, maybe initially through technical conferences that you may conduct to really sort of explore how this is being considered as part of the overall resilient solution portfolio, if you will. Next slide, please. The other thing, when we start to talk about roles and responsibilities, given the nature of these different events, means that as we go from a very localized event to sort of some what I call the major local or major regional, we're going to end up with more people involved, more organizations having an interest in helping to define what the objectives are. So this is really important to understand who will need to be necessarily involved in both post-event evaluation, but much more so on the upfront planning process and determining objectives and planning criteria. So I think the next slide starts to explore a little further. So the next slide, please. This is something that we consider this sort of draft, but this is something we started to sketch out much earlier this year in terms of a starting point for thinking about the various roles that folks may play within the state. Obviously, there, as we noted on the other slide, a federal dimension when we start to get into multi-state impacts or other, federal interests that, for example, the Department of Defense and the like in a particular state or community. But for simplicity and what can fit on the slide, we've got sort of a state perspective here. And I won't go through the details here, but what the point is there are a number of dimensions that could be quite helpful to think about how to link activities across these different interests and sort of focus, if you will, in terms of these needs around resilience, and how do we engage stakeholders effectively in this process across these different areas of focus, from at the broader state level, as well as at the commission's focus across that state, and then individual utilities and communities and the like. The next slide, please. So to kind of close, there's several questions that could be that you may want to consider thinking about. And again, in the context here of distribution grid investments affecting the system's physical and cybersecurity, it's an important starting point. So how are potential threats being assessed and translated into planning considerations? That's a pretty important aspect. Is it something like what Hawaii is doing, or is it something else? Is the state leading that? Is the utility doing it? Is it something the commission yourselves are facilitating? Is there a clear logical explanation how proposed investment directly or indirectly supports resiliency? There ought to be a pretty clear line of sight and logical discussion about how that fits, and that really gets to the third as well. So as proposals are coming forward, both in terms of distribution plans, longer term plans, but also in various rate cases or applications for funding, there ought to be pretty clear about how those particular investments link to the overall resiliency objectives. And to the extent that they're using some type of analysis like the bow tie I mentioned, they ought to be able to tie to whether this is investment is about preventing an outage or whether it's about mitigating the effects if there's a failure after the fact and being able to reconcile that. And then, as we talked about, how do we think about thinking about what's happening on the customer side or independent microgrid solution type solutions? How does that fit within achieving the overall resilience objective of that community, of that state? And do we have all the key stakeholders involved in an effective engagement process, including the local communities? So with that, I think I'm done, and I don't know if there's a little time for Q&A.
Terrific. Thanks. And I will also mention that I will also drop the link for NREL has a section on resilience on our website too, so I will just drop that in. So the first question that we have from the audience is, how can public utility commissions decide on appropriate levels of investments and resilience of distributed systems? For example, how can commissions determine whether proposed large utility investments is worthwhile and not just an expansion of a rate base?
So I think I would say twofold. It kind of builds on what I was mentioning just on the prior slide. So the first is having a clear understanding of what the objectives and by extension the planning criteria that have been identified for the state and in particular for that particular utility. And it may extend even to that utility in relation to particular communities or subsets of communities. And by understanding that, then you can start to tie those investments to that particular need. Through that analysis, there ought to be able to be consideration as to whether utility investment or the fact that customers may be or some independent development is addressing that need, and therefore the utility doesn't necessarily have to also build something, is something that can be considered as part of the evaluation of the planning and something that the utility ought to be able to describe in terms of how they've approached it. It's possible that you would still make a grid investment and the utility and the customer does something on their side as a redundant, which is that sort of plan B, if you will. And so being able to understand that and be able to reconcile that's important. Now, how do you think about accomplishing that, recognizing that there's never enough budget to do everything you possibly would want to do? That's where we need to have some prioritization methods. And the one that I think works best is one that that I think it has been used in California, which is around this risk spend efficiency model. So the risk being identified in terms of a number of different parameters. They use something called a multi-attribute value framework. So basically they look at customer interruption, so customer outage duration potential. They look at things like financial impact to customers, to even the utility loss revenue, but it's largely driven by customer or could be including society, but that starts to get really tricky. And then you have some other, there's some other dimensions in there as well. But obviously they've got a wildfire risk that has a pretty big potential impact. So you could look at, you can set up whatever is the appropriate attributes for your jurisdiction. And then from that, that sets up the risk side of it. So you get a risk score, a normalized risk score, and then you can apply your whatever the cost of the solution to that perceived risk, and then therefore you can start to rank order the investments based on the the benefit that you would realize from that potential investment. This can be done without having to do a very large, complex economic valuation of what those risks are. You can do this just in terms of number of customers impacted and potential duration, particularly for large events, because that's what you're trying to mitigate. And so that could really be a driver, and then any other factor you want to add into it as an attribute you could do without having to get into a complex economic analysis. So there's ways to get started on this. Obviously, you've got the tools to do the more sophisticated economic analysis, you could add it in as another factor. But that's what I would suggest. And so I would take a look at what California's done on their risk spend efficiency analysis, recognizing it's been adapted to wildfire, but you can adapt that to whatever aspects you think are important.
Okay. Do improvements that improve reliability always improve resilience? Is the reverse also true, that resilience improvements always improve reliability? And also, how do we value the added benefit that resilient solutions provide when reviewing these investments?
So, it's important to understand what we're defining reliability and resilience to be. If what we're saying is an investment that would prevent an outage, and forget whether the label is reliability or resilience, that and whatever that investment is about prevention ties to then, what threat are you trying to avoid? By hardening a pole to resist a hurricane force wind may also help you avoid a car pole accident, taking down that pole. So, hardening that pole, having, let's say, a steel pole rather than a wood pole, may be able to accomplish both. We characterize a car pole accident as a reliability event. We characterize a hurricane wind force taking down a pole as a resilient event. But I think that, yes, you can use some of the same prevention measures can address both. But I think you need to look specifically at what it is you're trying to avoid, and whether that, what you do for the reliability type causes, which tend to be things like car pole accidents and basically things like squirrels getting into equipment and tree limbs getting into taking down power lines, particularly at the distribution. Those can also have direct relationship to the kinds of measures you would use or solutions are also beneficial for the what we're talking about in terms of the kind of natural events that may occur.
Thank you. Going back to a little bit more of a detailed question from earlier, have you found any analysis or tools that help utilities or other entities prioritize investments in grid resilience?
So the bow tie analysis is I would say, a leading practice to start to identify both what the priorities are. It also, both in terms of prevention and then also mitigation, to the extent that, okay, so you harden the pole, in most cases it survives, but in, let's say, the most extreme Category 5 hurricane, it still comes down. Now you're into mitigation, you're into your Plan B mode. So that methodology is a leading practice on how to think about investments that then also incorporates your threat assessments and your risks that are exposed. So you can go through that risk spend efficiency based on that approach. So you do your threat analysis, then you do this bow tie analysis. As part of the bow tie, you're then also able to then incorporate and do a risk spend efficiency, which then allows you to do the prioritization. That kind of approach, I would say, is kind of the leading practice about how to think about this. And we do have several utilities across the U.S. employing this. The utilities in California do. I know the ones in New York have been doing it for some time post Sandy. I'm guessing there are others as well, but that's what I would look at.
All right, we have a little bit over 5 minutes. I'll try to get through 2 questions. So relatedly, the concept of potential impact of threats presumes the risk ranking is a subjective exercise. Are you familiar with any jurisdictions, perhaps Hawaii, that have any objective data to back up their risk ranking?
So Hawaii was more of a subjective process. It was kind of using a Delphi method where you had a lot of community and folks that are knowledgeable about the critical infrastructure, they're knowledgeable about, you had experts on the climate changes and impacts on the severity of the events that may occur. And so that was fed into a discussion, and as a result, they came up with that those rankings. From that point, once you understand that, then you can start to think about, well, those threats and what's the impact. The impact on the system then becomes much more of a quantitative exercise, if you will, as opposed to just subjective. I think it really just depends on what's the history. I think with some of the hurricane, I'm guessing, because we're seeing these more patterns in terms of the severity and what the impact on the system, I think there's a better understanding. I know from the work I'm supporting right now in California on wildfires, it's much more moving towards a quantitative analysis because there's a history being developed. So if you have events that haven't really happened, like in Hawaii hasn't really had a hurricane in almost 20 something years, knock on wood, but there's not a lot of history. But in other parts of the country, obviously, we've been seeing repeated, pretty significant hurricanes and other storm, say in the upper Midwest, that you could start to look at some history there and start to do some more quantitative assessment of what the impact would be.
Thank you for that perspective.
Mm-hmm.
So one question that has come up is, how do we resolve the tension between the robust information sharing that some voices in the utility industry say is critical to this area and protecting information to preserve cyber and physical security?
Yeah, it's a real challenge. I don't have an immediate answer because the cloak of cybersecurity and national security has come over a lot of that infrastructure, starting with transmission and then into key distribution substation level. I don't have an immediate answer, unfortunately. I think it's something that's going to have to get worked through. I got to believe that we, as has been the case in operations, that some folks can have a designation, because some of this isn't top secret, right? Some of this is just sort of classified level. I think understanding really what level of security is needed, and therefore what sort of agreements need to be put in place so that certain individuals can see this information and be able to assess it. I think my sense is that could be addressed. Because just knowing substation locations and transmission maps, that, by the way, used to be public information, but now have sort of gone under this cloak. I've got to believe you can have people access that under the right sort of agreements or constructs.
Great. We have 2 more minutes. I can give you another question, or if you have any final words, we'll take those too.
If there's another question, happy to entertain it.
Okay. Let's see. What role can distributed energy resources play in improving resilience of electricity systems?
Well, the distributed resources, I think, really twofold. One is how are those resources, energy producing resources, helping to satisfy backup power for customers? And what we've seen over the last couple of years, an explosion of the use of battery technology as an alternative for backup power, as opposed to some sort of diesel generator or gasoline portable generator or natural gas generator. So I think we've seen now, particularly residential, maybe small commercial, a lot more battery storage. In fact, Generac, the leading supplier of backup generation, stationary generation, added a battery division to their solution set here recently. So I think the trend is there, so that clearly comes into play. On the grid side, if we're talking about more of these community-based solutions, then I think we need to look at the role that community-based microgrids can play. And we have a couple of states that are actively pursuing these and looking at them. Certainly, there's the development in Illinois around the Bronzeville project, but we have in California, we have Hawaii, activities in New York and other states that have been pursuing tariff options around these, community-based or front-of-the-meter type microgrids. And I think that's an area to consider how that development may emerge. I have a paper with SEPA that I wrote with Jared Leader on community microgrid or multi-user microgrid tariff development based on the learnings out of these various states today that's available.
Wonderful. And if we can, we're going to move on to the next session with continuing with Mr. Martini, and if we can get Fritz Carl just to have a sound check while I pass it over to Lisa. Fritz, are you there? Great.
Yes. Can you hear me?
Sound good.
Great.
All right, so we have one more session with Paul talking about grid modernization planning. And then Fritz, at the end of that session, Fritz Carl will talk about the important issue for public utility commissions. What are the economics around the investment? Paul, it's your floor again.
Thank you. So building on what we've been talking about so far, now we're going to get into that intelligence layer that I was talking about. But it's more than just that. Grid mod tends to cover a wider range of that pyramid, and we'll talk more about that as we get into towards the end of this my section. So the next slide, please. As you've been hearing repeatedly, next slide, please. Thank you. So we really do believe that you need to start with what it is that you're trying to accomplish. So what we call in the grid modernization approach, the DSPX approach, as principles and objectives. The principles are those principles for your state, for your commission, in terms of what it is that you're trying to accomplish with your work. And so that's a good starting point. We call that level 0 because that already exists. Those are the things you have enumerated on plaques or in public spaces in terms of what you're trying to accomplish. Objectives derive from that, and these objectives relate to specific aspects of what you're trying to accomplish with respect to modernization, but modernization in the context of what goes back to those 3 overlapping domains in the distribution planning process. That is, what are you trying to accomplish with resilience and reliability? What are you trying to accomplish with DER integration or utilization in terms of non-wires or other, or customer choice as part of that umbrella? And what also are you needing to do around basic safety, operational efficiency, and the like of the grid? And how does modernization play into that? How do we think about the overlay of intelligence and more sophisticated capability to make that work? So that these objectives sort of really fit to that. The how part that we focus on in this process is around, based on those objectives, what are the capabilities that you want to accomplish? And I'll go through an example. Then that derives a certain functionality at a more granular level. And then that determines what the requirements that you need for the technology, and therefore then you could make technology choices to satisfy those requirements, that functionality which supports a capability that meets the objectives, and certainly within the set of principles for that state. So this is how we think about it. What we want to, the thing that I got there in the third bullet, it's really important, is please, please, please do not start the conversation with talking about technologies. Don't start talking about all the great thing that technology can do. It's because without context is really not going to be, get you too far in the conversation. Better to start talking about principles and objectives and working your way into capabilities and functionality, and then start to have a conversation about technology choices and what technologies can do. Because without understanding what it is you're trying to accomplish and how you're trying to address it in terms of executing on those objectives, it'll start to get long. The conversation will start to not be terribly productive. So with that, we have a multi-step approach on the next slide. And this approach really kind of breaks two dimensions into two dimensions that are interrelated. One is developing an overall strategy, building on that taxonomy on the prior slide. So what are the mission and principles that the commission is chartered with and moving to achieve? The objectives specific as relates to modernization, then therefore what capabilities and functionality. After that, there's this need to look at architectural considerations and strategies. This kind of goes in part to what I was talking about earlier, with thinking about, where does, say, microgrids fit in? How do we take advantage of that? How do we think about that structure? There's also an architectural dimension around how we think about the role of the communications, what type of communications, how does data fit, what are the various devices, how do we organize the information communication technology, the software platforms. We'll talk a bit more about that. So there's some architecture relating to how we think about systems coming together. And we also have an architecture thinking about the grid at large in terms of how we think about this somewhat different grid over the next 10 plus years. Then there's a sequence that then that strategy informs related to specific implementation plans. So that starts with taking these requirements from the functionality, developing those requirements. There's a technique called use cases that's used. You'll hear from folks at EPRI who've really brought this to bear, over 15 years ago with a lot of the smart grid activity. There's a lot of utilities in the industry using use cases. That's still being done, and to derive requirements. That's important. Then we think about what technologies we might need at a holistic level. How do we think about organizing those technologies into a system? And then you can start to then pick particular technologies, say through procurement processes and the like, whether you're talking about metering systems or reclosers, or even potentially looking at third-party solutions that might fit into the mix. That is, DER provided solutions, or other sort of software as a service solution, or in some cases, some are operations as a service. That's a little more sophisticated. And then a deployment plan. So how do you put these together into a roadmap for a specific nearer term deployment plan? There is a time dimension difference between these two. Typically, the strategy tends to be a longer term horizon, including a roadmap over conceptual roadmap over a longer horizon, say 10 years or so. And an implementation tends to be something very specific in the nearer term, generally less than 5 years in terms of its specificity. In some cases, it can go longer, but generally speaking, for grid modernization, we're talking about sort of a 5-year horizon. Now, it's entirely possible that in a particular jurisdiction that a utility will have proposed an implementation in a rate case or in a separate application, and there hasn't necessarily been established a strategy through a proceeding or the like, or the utility in their proposed implementation hasn't provided a strategy, hasn't provided a longer term context under which that implementation would fit. And I think here, what we're trying to point out that while you may not have gone through a strategy development process, although a number of states have pursued that, and then that would then inform these implementations. If you do have an implementation being presented to you, you should definitely require that the strategic context be provided, so that at least at a minimum, you're able to understand how they're thinking, what they're proposing to implement fits with and would meet the kind of objectives that you think are important. And whether you identified these objectives or not, at least the utility could propose what they believe the objectives are, and then you can assess whether they've got that right or not, and then therefore, through a logical path, be able to determine whether the investments actually satisfy that objective. So there's ways to work this in a couple of different dimensions. We're going to go into a little more detail in the subsequent slides on each of these aspects. So the next slide. Next slide really speaks to this idea of how do we take, and develop a set of objectives. And there's an example here from Ohio, and there's multiple examples actually in the Midwest that can be applied as several states have pursued similar efforts. But really what we're looking at here is there's a range of potential, kinds of objectives that may be drawn upon for a particular state, particular utility, and it's important to identify, what those are. This is a list that's sort of a generic list looking across the U.S. and we identified. This isn't necessarily the all-inclusive list. It's fairly inclusive, but each locale, each state is going to determine its own set of objectives. But it's important to use this as a starting point for any planning process, including grid modernization as well. Next slide, please. So here is a simplified version of how we think about objectives being converted into capabilities. And so if we had those three broad domains that I pointed out in that Venn diagram on earlier presentations, we have this reliability and resilience, we have safety and operational efficiency, and we have DER integration and utilization. Those tend to be the big buckets. Obviously, objectives are more detailed, as we showed on the prior slide, and they would map to these. And from that, then we start to look at, well, what are the capabilities needed? And the capabilities tend to fall in three categories. One is planning, so what additional planning tools or data or the like, or analytic computing power that's needed for the planning processes. What aspects of grid operations, including those things in the field in terms of infrastructure, would need to support grid operations. Those things we call market operations, but this has to do with things like managing demand response programs, non-wires alternative, any of those activities related to utilizing distributed resources or enabling those resources to participate in wholesale markets that may be required at the distribution level to enable would be part of the market operations umbrella. And again, there's a detailed set of capabilities that we've articulated. Here, what we're trying to point out is that historically, those areas that are shown in the black circles or half black are aspects that were part of the traditional planning process. The blue shaded aspects are those that are sort of the new areas that we've had to think a little differently, both in the planning process and how to address those in the grid modernization function. So, a quick poll, have clear modernization objectives of the type that I was showing been established in your state? In some cases, this may be through legislation or regulation. Has it been proposed by the utility? If it hasn't been in the state, or has it been by both? Not yet on either case, or it's not clear whether they have been established. Okay, good. Okay, so thank you. So let's go on to the next slide. Okay, so here's an example, and I need to pick up the pace because I think we need a little time for Fritz's presentation. So on the taxonomy example, starting with an objective here, an objective would be reliability. So improvement of reducing customer outage durations. And to the extent possible, it's great to put something specific in terms of a clear metric associated. So in this case, I'm saying second quartile, KD performance by 2025. The capability would be to improve the outage identification and customer service restoration, right? So there could be multiple capabilities. I'm just picking this one as an example. And to achieve that capability, here are the functions that are necessary. We need to do fault identification, we need to fault location, fault isolation, service restoration. Now, to do those things, there are a range of technologies that could be applied. Fault current indicators, outage notification for meters, outage management system, geospatial information system to kind of know, the location dimension, distribution management system or a SCADA system, some automated switches, and a work management system that's kind of truncated there, but work management system to direct the crews to go out in their service restoration dimension. So this tries to give you a sense of how this can flow, and therefore, if you're getting a proposal on grid modernization and somebody says, I'm trying to improve reliability, you ought to be able to see something that essentially allows you to get this sort of visibility on how any particular investment that's being proposed, let's say an outage management system, you ought to be able to trace this back through this sort of sequence to be able to say, well, outage management supports, service restoration and fault location and fault identification, as well as, so those three, which then ties to outage identification and, so on. So, being able to, to make this linkage is an important dimension, I think, that helps you in your decision making. Next slide, please. Now, the other thing that we talk about in grid mod is this idea of grid as a platform, and the idea that there are certain applications that the utility will propose, and they depend on an underlying core set of investments to basically enable. So what we call the grid operational systems and grid infrastructure, which we believe are core to a modern grid. And then there are these applications that are sort of optional that sit on top. And those optionality may be required in the sense of what the objectives are or the customer needs are for a particular jurisdiction or particular utility. But fundamentally, what we mean by core is that these investments support multiple sort of applications, whether it's inside the utilities represented by the blue, or for others like DER aggregators or microgrid developers that will need these various core systems for their applications, for their services that they're looking to provide. And then there are some market operational systems that go in hand as well. Things like DERMS that will become an important component if you are going to have some of these other DER services being provided and the like. Next slide, please. So this slide just, and many of you may have seen this slide, this just takes that concept and goes deeper. You can see the core components that we've identified here. This was developed over several years, and this is now, I think on the average, about 4 years old. And it seems to have sort of stood up to a lot of scrutiny. And again, this is to basically describe that as you go through this process, trying to understand which elements are sort of core to what you need to accomplish in your area, as well as those things that we call applications that are sort of modules that can sit on top of this core and provide value as needed, as identified in the planning process. Next slide, please. So this next slide is basically illustrating that you want to understand your starting point. And so you can take that diagram, as several utilities and commissions have done, and basically just do a very quick high level shading to get a sense of like how far along are we in our modernization on these various dimensions, recognizing in some cases you have field deployments or software deployments that go in modules or in the field, obviously by individual units being implemented. So these things can have a life where there's an evolution to them. But it's important to understand this. Now, typically, it isn't just left with this kind of a pictorial view, but rather there's a more detailed analysis that supports this high-level conceptual view. Next slide, please. So we talked about this hierarchy earlier today, and what I've done here is just shown where grid modernization tends to fall across the country in terms of the focus. And the reason I'm highlighting that with grid modernization with respect to microgrids is just that there's pretty sophisticated technologies that the utility needs to implement on their side, on their systems, to be able to make microgrids really work effectively in terms of what's trying to be accomplished with resilience and reliability. And you can see, as I noted earlier, that reliability and resilience really covers a large range of these kinds of investments, and then asset planning, where that tends to fall traditionally in its scope. So you can see that there's a need, as if there are different groups within a utility looking at these different dimensions. If you have different proceedings on these different topics, there are overlaps, and you'll want to understand those overlaps for a particular utility, for your particular state, to be able to understand how you can ensure that you get the most efficient and effective portfolio of investments. The next slide, please. Sequencing investment. This sort of waterfall type chart builds on the technologies that are selected. There's a logical sequence that might happen with respect to predecessor investments that are necessary before you do the next one. There are also, as I was talking about, these core investments and applications. Again, you have a similar sort of dependencies that you want to lay out. The other thing that some utilities have been doing that I think is a good thing to do, which is to also illustrate the value that customers realize over time in terms of the capabilities enabled, linking it back to those overall objectives. Now, that can get difficult in the early stage when you have core investments that you need to lay the core down and then add the applications that start to are much more sort of customer facing in terms of capability. But you can, and some utilities have done a nice job in terms of overlaying that customer value and benefit accrual, if you will, in terms of what they would see in terms of capabilities. Next slide. Thank you. Did we skip over the consideration? We can come back to that. Oh, that's right. We're going to do that at the end.
Great. Thanks, Paul. Next slide, please.
Hey, Fritz, can you move down your camera a little bit?
Yes. Absolutely. There we go. Is that a little bit better?
Just trying to keep you in the frame.
Okay. Is that better?
We'll see.
Okay. Maybe it's kind of an interesting. There we go. Maybe that perhaps a little bit more. Okay. Thank you. It's a pleasure to be with you all. So just to pick up on Paul's presentation, so volume 4 of the Modern Distribution Grid series includes a chapter on grid modernization, investment economics, and I'm going to cover some of the material from that chapter today. So I wanted to step back and start with a bit of motivation. Over the last few years, I think there's been growing consensus on what the vision for a future distribution system should look like. That is, modern distribution grid should be information-rich, flexible, automated, secure, reliable, and resilient. But there's still less consensus on the focus and timing of the investments to get there. And in particular, economic evaluation of grid modernization investments. That is, how distribution investments are evaluated in regulatory proceedings is a key hurdle in the transition to modern distribution grids. Next slide, please. So why is economic evaluation of grid modernization investments so complex and challenging? At a high level, I think there's at least four reasons. The first is the challenge of finding a balance between a holistic vision and investment strategy on the one hand, and the reality that many of the component investments of a grid modernization strategy will support different objectives and have different evaluation methods on the other hand. And the second challenge is maintaining appropriate separation between distribution investments in grids, investments in the distribution grid, and investments in resources. So investments in the grid that support distributed generation versus the distributed generation itself. The third is that many grid modernization investments will have joint and interdependent benefits. What this means is that the benefits are hard to isolate and they depend on other investments. And then the fourth challenge is uncertainty, including uncertainty over costs, timing of need, and technology maturity and potential technology obsolescence. Next slide, please. So in chapter 5 of the Modern Distribution Grid report, we tried to develop an economic evaluation framework to help address some of these challenges. So this framework has 3 stages: planning, deployment, and evaluation. The planning stage includes many of the elements that Paul already talked about. So in this planning stage, regulators and utilities develop and prioritize objectives. They set spending limits, so limits on utility investment spending on the distribution system. Regulators coordinate different processes. So this is the sort of the overlap problem that Paul just mentioned. So these would range from utility resource planning to utility rate cases. Utilities and regulators identify different investment needs, priorities, and timelines, with the needs linked to objectives and with performance metrics tied to those objectives. And as part of this process, utilities and regulators develop a taxonomy to categorize investments based on different investment drivers for the purposes of evaluating these investments. And I'll get into this in a little bit more detail in a second. Next step is that utilities make distribution investments. And then lastly, they evaluate investments against performance metrics and adapt investment strategies accordingly. This process of sort of continued evaluation and adaptation is really critical to this whole process, because it sort of goes without saying that we're never going to get everything right the first time. We're going to have to learn and adapt. And so building that learning and adaptation into the sort of the process through which we both evaluate and sort of deploy investments is really critical. Next slide, please. Next slide, please. So somehow the figures didn't show up, but within this framework, just to give a little bit more context for how you can target economic evaluation. So within this economic framework that we've developed in this report, investment categorization is one of the most important elements, and I wanted to give a little bit more detail about what this means. So for categorizing investments, we have 4 categories in the report. Core platform investments, so the core investments that Paul just mentioned, have joint and interdependent benefits. So in this, for instance, this might be an advanced distribution management system or more expensive investments in SCADA systems. Investments that are needed for compliance with reliability and safety standards, or that are needed to proactively integrate distributed energy resources. So these might be, for instance, circuit upgrades in parts of the distribution system that have chronically low reliability. Third category is investments that have net customer benefits, meaning that these investments will lead to net benefits in the form of reduced bills for some or all customers. And importantly, this is not the resource itself, it's not the distributed generation itself, it's the investment in the grid to support the distributed generation. And then lastly the last category is investments that are driven by customer choice. These could be things like community investments in undergrounding or customer interconnection costs that are triggered through the interconnection process. For joint benefit and compliance investments, we're arguing for using a least cost best fit methodology. And what this means is that the investments, perfect. And what this means is that previous slide, please. What this means is that we choose investments that provide the most benefit and functionality at the lowest cost. There's a lot of difficulties in applying a traditional benefit cost framework to these kinds of investments. For investments that provide net customer benefits, we use more traditional benefit cost analysis. For customer choice investments, we assume that they're self-supporting, meaning that they're paid for by customers and that they're assumed to be cost effective. So from a regulatory perspective, we don't need to do cost benefit analysis on these. So this approach kind of builds off of and roughly mirrors the approach that the Hawaiian Electric Grid Company used in its grid modernization strategy. Next slide, please. So there are lots of different approaches to investment categorization. So here's a quick illustration of a little bit more detailed approach to categorizing investments for the purposes of evaluation. So we categorize first step, we categorize investments by objective. So this is the objective making process that Paul talked about. So we have 4 objectives here. First, our core platform. These are the investments that will enable other kinds of investments. Economic efficiency. So these are investments that will reduce costs and improve the sort of overall cost efficiency of the system. Third would be resources that help to integrate distributed energy resources. And the fourth would be reliability and resilience. And then we organize investments by different investment drivers and evaluation methods. So core, minimum standard, and policy-driven DER integration kinds of investments are going to fall under this least cost best fit approach. Grid modernization investments needed to support time-varying rates, utility programs, and distributed energy resource integration and non-wires alternative procurement will fall under a better, more traditional benefit cost analysis framework. And then customer-driven DER integration and customer-driven reliability investments will be self-supporting. Next slide, please. So just a quick summary to wrap this all up. So first, economic evaluation of grid modernization investments is complex and challenging. It's important to have clear objectives, robust and coordinated planning, so dealing with some of the overlapping parts of the utility regulatory process, and having targeted evaluation of investments. All of these can help address some of the challenges that we're facing with evaluating grid modernization investments. Targeted evaluation, we can use targeted evaluation to sort of help better kind of evaluate these different investments. So we can use least cost best fit for investments that have joint and interdependent benefits, or for those that we're complying with standards and policy mandates. We can use benefit cost analysis for investments that we're expecting to have net customer benefits. And we can assume that benefits that are driven by customer choice will be self-supporting, and from a regulatory perspective, don't need the benefit cost analysis. Planning, having a robust planning, spending limits, so setting limits on what utilities can spend, pilots, and having ex post performance assessment processes in place are all tools for incorporating risk into the investment decision making process. And lastly, and probably most importantly, is that building in performance metrics at the beginning of this process is really critical to supporting the process of learning and adaptation, which is going to be critical throughout the grid modernization investment process. Next slide, please. So to close, a key part of making from a regulatory perspective, a key part of making the right or smarter grid modernization investments is in asking the right questions. So this is a list of questions that states and regulators can ask of their utilities, and I'll just go through this really quickly in the interest of time. So first, to Paul's polling question, have objectives been established in policy or regulation or proposed by the utility? It sounds like the answer is in a lot of states is probably no, but this is a really important first step. Second is which objectives are supported by different grid modernization investments, so mapping in different investments to different objectives. Third is how should planning processes affected by grid modernization be coordinated? So for everything from utility rate cases to the distribution planning process, how can we better coordinate these processes? So for instance, putting them in a single proceeding or using an integrated proceeding to sort of integrate these. Fourth, what are the drivers of different investments and how should they be evaluated? Fifth, what is the pace and scope of change expected over the planning period, and how does the grid modernization planning process address the needs that we're expecting over the planning process? So for instance, if we're not expecting a lot of distributed energy resource adoption, then do we need a lot of investments to support it? Next, what are reasonable levels of spending and rate impacts for grid modernization investments? How do we set appropriate levels of spending? Next, what performance metrics should be used to evaluate the investments? How should risk management be incorporated into investment prioritization and decision making based on, for instance, things like technology obsolescence? Do we have a clear starting point for modernization? And lastly, do grid modern plans incorporate the flexibility needed to deal with uncertainty, both in our needs, for instance, if we have rapid electric vehicle adoption, or to be able to better incorporate emerging technologies as sort of different technologies develop. With that, I will close, and I think we're going to open up for questions.
Thanks, Paul and Fritz. So we have some good questions for you here. Let's start with really good question. How can investments that enable distributed energy resources as part of a modern grid be balanced against the impact on cost to low-income customers who are unlikely maybe to ever install their own distributed energy resource? Let's start with an easy one for you.
Well, I think, and this kind of ties to both what Fritz and I were talking about, which is it really needs to understand what the objective is. And in many cases, you need to start with what is the state identified in terms of societal objective with respect to why the policies related to distributed resources were being implemented. So if there were incentive programs or there were tax credits or the like, those rationale for why that was put in place sets the context for why you then may need to do an investment and why it may make sense from a broader perspective, from a societal perspective, that the legislature sort of set out implicitly, if not explicitly, in why these other incentives may be in place or policies that were put in place. Now, where that comes as a challenge is that's not going to show up in some benefit analysis, right? And this is where this gets really complicated. And then if you're not able to make that sort of determination that there isn't a cost savings running, flowing through the utility as a result, this is a societal benefit identified by the legislature, then you're in that camp that Fritz is talking about with respect to, the best fit, meaning the need was identified, and then you got to think about, is this the right solution for what you're trying to accomplish? I don't know, Fritz, thoughts?
Not really anything to add except for I think this is a balancing act, and in a lot of cases, regulators are not necessarily in the driver's seat, as Paul mentioned. In a lot of cases, these are coming through as legislative mandates that regulators are having to deal with and trying to sort of work out the equity issues with. And I think that's going to be a really, really important challenge for the regulatory community over the next decade.
A related question.
Yeah,
go ahead.
No, please, Lisa.
All right, well, it's a related question, so you could chime in again. So this question was directed to Fritz. Can you provide an example of how regulators have set spending limits or rate impacts for grid modernization projects?
Paul, I'm going to defer to you on this one.
Well, in the Hawaii example, so in Hawaii, Hawaiian Electric had proposed a smart meter program and had been denied 3 times. And on the last one, the amount that was proposed was somewhere in the neighborhood of $600 million, and which was a large amount in relation to the size of the utility. And there was an understanding that that was just too much. There was an interest in smart meter, but it was too much. So then there was some discussion, more one-on-one with the utility. Nobody having a specific number that was being discussed, but at least some sense that, what might be a more reasonable number that could be, would make sense within the context of rate impact. And I think through just dialogue, without anybody having to give specific numbers, there was a better understanding that something on the order of half of that amount probably was something that could probably be accomplished. And could you go back to the drawing board and be more thoughtful, Hawaii Electric, about how you would approach this so that we could maximize the value of that investment? And that's what led to that grid mod strategy and then their ultimate implementation plan. I know it's a very tricky thing because nobody's going to tell somebody specifically what is achievable, but I think, as Fritz said, to the extent that there could be some parameters around it, I think what we want to avoid is, for example, what happened in California with SoCalEd's request, where they had $900 million worth of 4 kV upgrades that nobody was expecting, was really, at the end of the day, obviously got scaled way back, but it led to a lot of consternation, led to a lot of, really frankly, time wasted that could have been addressed on the outset by just saying, look, here's how we think about where that kind of stuff fits. We don't think that's in modernization, and or look, rate impacts, hey, you need to be focused on this. It needs to fit into context. We're not thinking, big numbers are going to be achievable or reasonable to do. We kind of just set some general guidance, and I think that could have been mitigated.
So you said it. Oh, go ahead, Fritz.
I was just going to add one thing. I don't actually, I don't know why this process doesn't, that more states and state regulators don't kind of think about setting some process to set spending limits and sort of develop an understanding and communication with utilities early on in the process. Because the two examples I was thinking about, that that having this dance between the regulator and the utility, where the regulator says, bring me your proposal, and the utility comes with this gold-plated thing, and the regulator rejects it, and having to go through a year's worth of this process seems really inefficient relative to sort of starting out at the beginning with a shared understanding of what we're doing, what the sort of general limits are on spending, how much relative, so the regulator has an understanding of relative terms how much things cost. I just think this would be really helpful.
Yeah.
All right, we have 3 more questions that I'm going to try to get to in 5 minutes. So let's see how fast we can do it. You said at the end of the presentation, Fritz, that performance standards are really important. And so how do you think grid mod investments would change by utilities if commissions adopted performance-based standards rather than a focus on sort of a rate-based standard?
I think what one of the things that performance-based standards help to drive is more of a focus on performance. So as Paul said, sort of at the beginning, not talking about technology, just setting up what you want the system to be able to do, and then setting out the performance metrics on the basis of the functionality that you want the system to have, gives you a better, sort of moves you into kind of a more narrow focus on functionality rather than on how many meters you're installing or whatever the technology basis is. But I just think moving toward more of a performance approach gives the utility a little bit more flexibility to figure out how they're going to do it, but at the same time sort of holds the utility to account.
Yeah, I mean, for example, in the example I provided, say on outage, was moving to second quartile on Katy. That sort of metric is something that you can actually go back and measure. And did those investments actually enable that or not, and close that loop? Often we don't have that feedback loop that says, okay, you've made these investments, give it a year or two to get some experience, but did that performance actually get accomplished? Now,
so Katy is customer average, interruption, duration, something.
Yeah.
All right, you got to put a quarter in the acronym jar.
Yeah, exactly. But that feedback mechanism, obviously in the states that have some sort of performance-based rate making have these, but states that don't still can do the same thing. That is, in these sort of annual or biannual reviews of, say, smart grid reports that some states have, like Oregon or others, you can basically have a, kind of a follow-up on, so is it doing what you said it was going to do? What benefit have we gotten?
Okay, we have time for one more question before our last presentation for the day. So when you have multi-state utilities, like we have in many parts of the country, including in the MISO footprint, what type of cost allocation have you seen, or what have you liked in terms of cost allocation for these so-called core components?
Well, the example that I'm most familiar with is some of the utilities that in the New England states that have had this issue, and there are really sort of 2 things there. One is the states are obviously moving in different time sequences in terms of considering these investments. So one state may be sort of addressing a proposal in some cases a year or 2 before the other. In one example I'm familiar with, there were 3 states involved having to do with an ADMS solution. And so one state was making a decision on their portion of it a year or 2 before the other 2 states. So that's an issue, is understanding the coordination, because in fact, if you're the 3rd state, it may be fait accompli. There isn't much that you're going to say no about. So So I think that's one, is just understanding if that's the case, having some collaboration about how this would work. The second is, it can be done based on percentage of customers, is one approach. So if one state has the majority of the customers related to what that system is going to support, then you could do that. Now, this can get really tricky in the Midwest because, for example, First Energy, which is what you want to have happen, uses an enterprise set of applications for all their operating companies. So their ADMS supports all the various utilities and operating companies within those utilities across all the different service territories. And so then that gets really complicated, is to figure out how to do that allocation. So I'm not saying this is simple, but there are ways to think about how that would parse. But I would start with trying to get coordination amongst the various commissions that may be taking up these investments, and understanding the sequence so that you know where you fit in that sequence, and then try and work out, perhaps with the other commissions, how to think about the allocation, so that not just depending on the utility to make a proposal, but maybe you have some thoughts that you want to put forward and have the utility address.
Fritz, any last words on that topic?
Nope, that was a great response.
All right. Thanks again to Paul and Fritz. And we're on our last presentation of the day.
Great. Thank you.
All right, Carrie, do you want to say any words here about the survey, day 1 survey? And hopefully you'll put up also the day 2 survey.
Thanks, Lisa, for the cue. Yes, we, sorry about that earlier, but the day 1 survey link was broken because I included a period, but I have included the correct link now, and then I will get the day 2 survey posted right now again. Oh, I accidentally clicked at that time. So we'll get that to you. But again, we had about 30 people take the survey yesterday, but we had over 100 people. We had almost 130 people on. So we really need to get those participation numbers up. We really want to hear from you if this was useful for you and how we can make it more useful for the other regions in the future. So thank you for your time with that. So I will be sending out that link now.
All right, thanks, Carrie. So my presentation today will synthesize approaches that states across the country are taking on distribution planning, with a focus on regulatory practices by public utility commissions. But first, we have a poll for you. All right, of total capital investments that investor-owned electric utilities made in the last year in 2019, about what portion does distribution represent? Is it 10%, 15%, 20, 25%, or 30%? And we'll show the correct answer in a moment. Oh, you all are good. Well, you're so close. So the answer is 29%, so about 30. So you are super close. Well done. And that's according to the Edison Electric Institute. And this is one of the reasons that states are increasingly paying attention to distribution planning. Next slide, please. All right, here's what my colleague Juliette Holmer and I will be covering during our presentation. First, I'll put distribution planning in the context of other electricity planning processes and talk about some drivers for increasing regulatory engagement in distribution planning. And next, I'll provide a snapshot of state objectives and requirements and some of the common procedural and substantive elements for distribution plans, particularly those that include distributed resources. And then I'm going to drill down into 2 areas that were discussed earlier today, but from a regulatory perspective instead of a technical one, which you heard earlier: procurement strategies for non-wires, alternatives, and hosting capacity analysis. And then Juliette Holmer will wrap up with several other regulatory issues, data-related requirements, stakeholder engagement, how to get going with a distribution planning proceeding, and emerging issues. We provide hyperlinks throughout the slides that are posted on the Berkeley Lab website look at the link that we put in the chat box. So you can look at the citations and learn more and maybe adapt for your own state. And in the back of our deck under extra slides, we include state-by-state approaches with lots more links. Next slide. So let's start with electricity planning and drivers, and one more. Next slide, please. All right, so distribution planning is really talking about the local grid. We're assessing the physical and operational changes that we need to address. It's an annual process to identify and define distribution system needs, to assess possible solutions, and then select the projects to meet those needs. There's a long-term capital plan for the identified solutions, and that's typically over a 5 to 10 year period, and that's refreshed every 1 to 3 years. Integrated resource planning, where it still applies in your region, it identifies future investments to meet the bulk power system needs. And as part of that, utilities can consider multiple scenarios for both loads and distributed resources, and the impact that has on the need for and timing of utility resource investments. And finally, transmission planning identifies future expansion needs for the high voltage delivery system and options for meeting those needs. And there are other planning practices, energy efficiency, demand side management, increasingly electrification, and state climate plans. So through an integrated planning process, these multiple load and resource scenarios can be considered in a consistent way throughout the distribution and bulk power systems. Next slide, please. So why might states be interested in distribution planning? As we revealed in our poll, one reason is that investments in distribution systems are really large. For U.S. investor-owned electric utilities, they count for the largest portion of CapEx, some $39 billion in 2019. Next slide, please. So states are responding to a variety of other drivers for improved planning. First, we just have increasing deployment of distributed resources. Some of this is disrupted. We're not disruptive. We're not just, planning for all of this. These are things that customers are bringing into play. And that's happening because of reduced technology costs, but also state policies, new business models that utilities and third-party providers have, and in customer interest. Storage and microgrids, you'll hear more about that tomorrow, connected at the distribution level. They're increasingly being deployed to improve resilience and reliability of the electricity system. And with new technologies and systems, we have a lot more data. Luckily, we have better tools to analyze that data. We can harness that to improve planning and operating distribution systems. As you all know, many utilities are proposing to update aging grid infrastructure. Distribution planning can help put all of those proposals in a much broader and longer term context. And there are areas across the country, certainly in the MISO footprint, with high levels of variable energy from wind and solar. And those areas have increasing need for grid flexibility. Resources at the distribution level can help, like storage and demand response and energy efficiency that are targeted at the right times and right places, in tandem with natural gas plants for flexibility. There's increasing interest in utilities operating distribution systems more efficiently. You heard from Kevin Schneider yesterday about conservation voltage reduction and volt bar optimization, all to reduce energy waste on the distribution system. And non-wires alternatives to traditional solutions may provide net benefits to customers in certain cases. Next slide. So there are other potential benefits from improved planning. And for me, first and foremost, having that holistic and longer-term picture of utility plans for distribution capital is really important before the utilities actually make the investments and they show up individually in rate cases or in rider proceedings. Second, it provides opportunities for PUC and stakeholder engagement, and in a meaningful way that can improve outcomes. Distribution planning also can consider a broader range of possible futures, consider solutions that can achieve the desired system at least cost, considering risk, and maybe motivate the utility to choose those best solutions for customers. and also enabling consumers and third-party providers to propose grid solutions and participate in providing grid services. That's an increasing focus of a lot of states. You'll see that in a lot of state proceedings. Next slide, please. So, as Paul has mentioned repeatedly, next slide, please. States, it's really important to establish their objectives for distribution planning, and hopefully the practices they set follow those objectives. So, for example, in Michigan, the Public Service Commission initially set 4 objectives: safety, reliability and resiliency, cost effectiveness and affordability, and what they've called accessibility, which includes reasonably accommodating service to new or existing customers without causing any major network upgrades because of some kind of underlying infrastructure challenge. And the Commission is also exploring, as part of that, resource diversity as part of accessibility. Turning to Nevada, the legislature there focused on contributions to meeting local generation and distribution capacity needs, as well as benefits for safety, reliability, and cost savings. And in Minnesota, the legislature established grid modernization objectives around reliability, security, and energy conservation and demand response opportunities. And the Public Utility Commission set several objectives for distribution planning. Next slide, please. Last year, the Electric Power Research Institute reported that there were legislative or regulatory efforts underway to modernize the distribution planning process in half the states in the country. The most common requirements related to data sharing and transparency, hosting capacity, non-wires alternatives, including identifying which grid needs may be candidates for solutions, specific requirements for distribution plans. That included documenting the process and the utility's capital investment plan, as well as establishing procedures to better incorporate distributed resources and locational value to systematically analyze costs and benefits of distributed resources to determine the net benefits they can provide for specific areas of the grid. Next slide, please. So here's a snapshot of distribution planning requirements across the country, both legislative and regulatory actions. We published the first version of this table in our 2017 report on state engagement in electric utility distribution planning. We revised it for an update of that report a year later, and we updated it again for this presentation. And what we found is that the changes reveal a rapid increase in the number of states and the types of requirements over this short period of time. Next slide. So here we provide links to state filing requirements for both distribution and grid modernization plans. And some states have both, and some states are in the process of sort of merging those. So these are just examples. The list doesn't show every state that's taking action or every action that each state is taking, but it gives you a good sense. And as we showed on the last slide, at least 16 states and the District of Columbia have established requirements to file distribution plans or grid modernization plans or both. And utilities in several other states are filing grid modernization plans on their own motion. By our count, at least 8 states, plus the District of Columbia, require some sort of hosting capacity analysis or maps, or both. And about a dozen states require utilities to consider non-wires alternatives for certain types of distribution needs like load relief and reliability, and then to consider the locational value of these resources. And several states are actually providing explicit benefit cost analysis frameworks for evaluating non-wire solutions. And states may require utilities to actually file handbooks. This is all about providing transparency on methods. It's much the same as we've had for decades for demand-side management, where those frameworks are rooted in the cost-effectiveness tests that are based on avoided costs. Next slide, please. So I've pulled together on the next several slides a synthesis of the range of both procedural and substantive requirements for distribution planning. So let's, starting with here with procedural elements, really the first consideration is, well, how frequently should utilities be making these filings? And there have been adjustments over time within states as they gain some practice. Typically, utilities are required to file a distribution plan every year or every 2 years. And some states allow more time between filings. For example, Nevada requires utilities to file a distributed resources plan as part of the utility's integrated resource plan, so the filing frequency aligns with that at 3 years. There are some other considerations as well with respect to how frequently utilities file plans, including alignment with the utility's capital planning process, the workload both for the utility and the commission and stakeholders, and a timeline that facilitates both making and tracking progress on goals and objectives. So is it too short a time frame? Is it too long, or is it just about right? So a lot of things to balance here. Another important procedural element is the planning horizon. That is, how long a time period are we looking at? So typically there's both a near-term action plan, which can be 3 to 5 years, and there's also a long-term plan that can be 10 years or more. Among the considerations for setting that planning horizon are interest in understanding both short-term and long-term investment, and coordination with integrated resource plans where they exist, including the term of the action plan for the integrated resource plan and matching that up. At the same time, we recognize that distribution planning is far more granular. Location-specific needs really change on a shorter time frame than bulk power system needs, and they're, I think, also both are fairly uncertain. So there's sort of arguments for a shorter and a longer time frame. Stakeholder engagement is something that Julia is going to cover shortly in this presentation. Next slide, please. And those requirements really vary quite a bit. All right, confidentiality is another sort of procedural element that commissions, address in every proceeding. In the case of distribution planning, one area where this really comes up is with hosting capacity maps. Some utilities display the feeders in the maps with buffer zones to mask the exact route details because they're concerned about some information related to critical distribution infrastructure. But in New York and California, they've worked this out, and the maps there show feeder routes without buffer zones. So commissions have gone different ways on this issue. And of course, there's a host of competitive and proprietary considerations that raise confidentiality issues like the ones I've listed here. Next slide. All right, let's turn to substantive elements. What do the filed plans actually need to include? So the requirements include providing baseline statistics on equipment and system components. And for example, there may be an interest in not just understanding the basic elements, but what advanced components do you have? How much SCADA do you have? Where is it? How many advanced meters have you deployed? Versus just like the basic meters. Additionally, metrics like SAIDI, SAIFI, and CAIDI that measure the duration and frequency of interruptions, both on the system and for customers, equipment ages and conditions, and historical spending by category to provide some context. Also included is a description of the utility planning process. That includes load forecasting, focusing on projected peak demand. Ideally, the utilities were applying scenarios increasingly to account for various drivers of load changes. That includes historical load growth, weather history, customer planned load additions, and disruptive events like we're experiencing today with COVID. Utilities also consider new sources of demand, whether it's increasing levels of air conditioning, which we're seeing in various parts of the country, and in pretty much all over, we're seeing increased levels of electric vehicles, and also the growth of other distributed resources. The utility is conducting risk analysis on its feeders all the time and substation transformers, concerned about potential for overload. And as part of the distribution planning process, they're developing a mitigation plan to address all of these concerns. Ultimately, the utility develops a budget for planned capacity projects. They've got to take into account all sorts of things from the health of the distribution assets already on the system reinforcements that may be needed, upgrades that may be needed to meet capacity needs, reliability and other criteria, and the new systems and technologies that the utility is planning to put in, for example, for grid modernization. So they've got to prioritize this. They can't do everything all at once. So they use criteria to prioritize the projects that ultimately that they design and construct. And I don't want to lose sight of the fact that these distribution plans should have a pretty strong emphasis on distribution operations. That includes the very important task of vegetation management, as well as how the utility is going to manage reliability and resilience events. Next slide, please. So 2 key drivers for distribution planning requirements by states are consideration of distributed energy resources and grid modernization strategies. So these are really driving some of these distribution planning requirements. So with respect to distributed resources, utilities are forecasting both the types and amounts that they expect to see on their system and the net load impacts on the grid. Also key is analyzing hosting capacity and non-wires alternatives, and I'll provide example state requirements for those in just a moment. As Paul talked about, distribution plans inform grid modernization strategies and vice versa. In some states, regulated utilities are seeking some sort of blessing, such as a certification from the Public Utility Commission in advance of making major grid modernization investments. Another important element of plans is the action plan. You can consider this a near-term roadmap for the utility's capital investments and operational expenses for major technologies, systems, tools, and activities. And then commissions may have some additional requirements, for example, requiring a long-term plan that includes the utility's long-term vision, understanding where integrated resource planning applies, how distribution planning is coordinated with that, understanding what strategies utilities are using to engage their customers in the plan. Are they learning about their preferences for grid services? Are they learning about ways that customers would be willing to provide grid services if provided the opportunity to do so? There's usually some requirement to summarize the stakeholder engagement in the planning process. And then it's a typical place to put proposals for pilot programs. For example, for assessing non-wires alternatives, for piloting time-varying pricing, like critical peak pricing, for example, and for managed charging for electric vehicles. Next slide. So this graphic is from Xcel Energy's 2019 Integrated Distribution Plan. And I really like it because it's very simple and it shows the evolution in distribution planning practices. So starting at the bottom with a traditional focus on peak demand forecasts, and then layering on top of that forecasts of distributed resources, and then considering multiple scenarios, both for loads and resources. And then the more advanced steps from there are more formally integrating distribution planning with both power system planning and routinely considering non-wires alternatives, including their locational value. And at the very top is harnessing distributed resources for a wide range of grid services, not just, for example, for load relief or reliability. And this is something that Natalie will talk about more tomorrow. Next slide, please. So let's dive briefly into requirements for procuring non-wires alternatives. Next slide, please. So just as a reminder, these are options for meeting system needs related to load growth, reliability, resilience. There's really a range of options. It could be a single large distributed resources like a big battery, or it could be a portfolio of distributed resources like a battery, together with demand response and targeted energy efficiency. Distributed resources can provide load relief, address over or under voltages, reduce interruptions, enhance local resilience, and meet local generation needs. And there's promise that these non-wires solutions could reduce utility costs by either deferring or avoiding infrastructure upgrades, or putting solutions in place incrementally to provide a flexible way to address the uncertainty that we have in load growth, understanding what that's actually going to be. And you could potentially avoid some large upfront costs for forecasted load that may not actually show up. Typically, the utility is issuing a competitive solicitation for non-wires alternatives for very specific system needs, and then compares those bids to its planned traditional grid investments like a substation transformer, to determine the lowest reasonable cost solution, and very importantly, considering risk. Next slide. So to provide greater transparency and a more systematic process, some states have required regulated utilities to do two things. One is develop predetermined criteria for the kinds of capital investments that will include consideration of non-wires alternatives, and two, regularly assess opportunities to use them to defer or avoid large investments. For example, in New York, regulated utilities must routinely identify distribution project candidates and then screen potential non-wires alternatives using established suitability criteria, including project type, timeline, and cost. Next slide, please. So here's an example of setting needs and considering distributed resources in competitive solicitation to meet certain types of distribution needs. The need here identified is most often a load reduction quantity. So we're talking about, load reduction in megawatts that would enable the utility to defer or avoid a specific capital investment. The identified need includes the date by which the non-wires alternative would need to be operational and the time periods during which it would need to reliably operate. Next slide, please. California has established a distribution investment deferral framework that Debbie mentioned earlier today to procure distributed resources where they can cost effectively defer or avoid traditional investments. The regulated utilities publish a grid needs assessment annually that identifies grid needs for the next 5 years. And at the same time, utilities also must publish a distribution deferral opportunities report that identifies locations where non-wires alternatives may be a feasible and cost-effective solution. And by December 1st each year, the utilities file a list of distribution investment deferral opportunities, and they request the Public Utilities Commission approval to issue competitive solicitations for that. Next slide, please. All right, finally, I'll cover one example of hosting capacity analysis requirements. Minnesota. So in Minnesota, they established their policies and regulations on hosting capacity analysis over the past 5 years. It starts with a state law that requires the largest utility, Xcel Energy, to analyze hosting capacity for what they called small-scale distributed generation. And the commission defined that as a feeder level analysis annually for solar PV at or below 1 megawatt. And the analysis needs to be the level of detail that's sufficient to inform both the utility's distribution planning and the utility's potential distribution upgrades for efficient integration of distributed solar. So far, the utility has filed 4 hosting capacity analyses, and each time the commission reviews the analysis, it provides guidance for improvements for the next cycle of analysis. Next slide, please. So, for example, the commission required the most recent filing to include mitigation options and costs. So don't just tell us, where you're out of hosting capacity or where, it's still plentiful, but tell us where we're running out, what can we do to mitigate that and what would it cost? So it's very interesting because the utilities found that for about half the feeders that they analyzed, hosting capacity increased by an average of 1.9 megawatts each, with either no cost solutions or solutions that were quite low cost, under $5,000, for projected over voltage or thermal violations. So these are the most common. And so recently, the commission adopted a long-term goal to use hosting capacity analysis in fast-track screens for the interconnection process. So the analysis that's due from Xcel Energy in a couple of weeks must include cost estimates for more frequent updates for that use case, and also a cost-benefit analysis for other advanced applications for interconnection. In addition, the utility is going to begin exploring analyzing loads like electric vehicles in hosting capacity analysis to support the state's goals for transportation electrification. And that's something that other states like California have already begun doing. Next slide, please. I think we are on to Juliet's portion of the presentation. Juliet?
Okay, hi everybody, happy to be here. I'm Juliet Homer from Pacific Northwest National Laboratory. And I'm going to talk about data-related requirements. So next slide, please. So as different states are moving into these distribution system planning dockets, a key thing that keeps coming up is data, and that's something we've talked about today and yesterday. But there are a lot of issues about data that are being addressed, namely who has it and who gets it. I think the Hawaiian Public Utility Commission said it well in an order. They said they recognize that limited data visibility could lead to inefficient customer and grid investments. So this is one of the reasons that the data issue is being addressed. And when we talk about data availability, there's really two different types. One is customer usage data, and then the other is system level data. So with customer usage data, it's really about making customer AMI data available to both customers and third parties to support decision making. And some states are requiring utilities to use or consider using the green button framework. And that's really got two parts to it. The first is a part that's called Download My Data, and it's a standard that enables customers to download their own AMI data. And that's a little bit more common, but there's another aspect to the green button data, which is Connect My Data. And this data is in a data exchange protocol, which allows the automatic transfer of data from utilities to the third parties upon customer authorization. And then some states, as they're sharing customer AMI data, they use the 15 by 15 rule for aggregating customer data. And that basically says that if an aggregated sample is shared, it must contain more than 15 customers, and no single customer can represent more than 15% of the total aggregated data. So it's a way to share data, but also protect customer privacy. So also next, talking about system level data, this is something else that's coming up in a lot of these proceedings. And as Lisa talked about hosting capacity maps, I mean, that's an example of that where, you know, the system level data is being made available to developers and others. And I'm going to talk through a few examples because this is an important issue around data. So next slide, please. So I think New York is a good example of being very transparent with data. You know, they've opted for this distributed system operator model. And the picture here is an excerpt from a newsletter from the Joint Utilities of New York, and it's got a link to some data sharing portal. And so each utility has, you know, links to their hosting capacity maps. And then if you go to the Joint Utilities New York website, it has links to all of these different types of data. And as you know, as we look around at the different dockets, this list here, these little bullet, you know, punch boxes, it really incorporates kind of what we're seeing in terms of the types of data that are being requested and contested in some cases, or talked about. And you know, these are things like just the plans themselves, the distribution system plans. What are the capital investments the utilities are looking at? What are the planned resilience and reliability investments? Reliability statistics, hosting capacity, identifying the beneficial locations. You know, where on the system would it be most beneficial to have DERs installed? Load forecasting, non-wires alternatives, and others. So let's go on to the next slide. So Lisa talked about the California process, and it's an interesting one where they do, you know, the utilities do these grid needs assessments, and they look through their system and say, okay, here's what the grid needs, and then they do these distribution deferral opportunity reports, which are like non-wires alternatives, and these are the opportunities to defer traditional investments. So along with these filings in California, they're also required to make data sets available. And so this slide lists those data sets that are required to be made available by the California utilities, and really broken down into 3 categories. The grid needs, and those are all listed here, that type of information. And then in terms of the potentially deferrable projects, information on the planned investments that could be deferred, and then information on what candidate deferrals, you know, kind of the characteristics of projects that could be candidate deferrals. So that's California, and you can take a look at that order that's linked here, and it's got all the details of the data that's required. Next slide, please. So as we move on to the District of Columbia as an example, so District of Columbia had this whole MedSys process, And as part of that, they had a data information access and alignment working group. So a working group that was focused on these issues of data access. And that group came up with a list. Basically, they said, here's a long list of all the things that we'd like, all the data sets that we'd like access to. And the commission required a data sharing portal on PEPCO's website. But what's interesting is, not all of the data sets that were requested were going to be made available. And as someone asked the question before, there are these security issues, and I think each state is handling that in a different way. But as you can see, it's really small here. But certain types of data here require a non-disclosure agreement. If you look there, the load data requires a non-disclosure agreement. The working group said they would like to know about beneficial locations for investments, and the utility replied that information is not available yet. Moving down to the second one, there's a whole host of information that they require secure access in order to access the data sets. So it's not easy, and each state's doing it in a different way, but I think District of Columbia has been thoughtful about it, and it's an interesting example to consider. So next slide, please. So we're going to talk about stakeholder engagement. You can go on to the next slide. So stakeholder engagement is often required in distribution planning before a plan is filed, as well as after the plan is filed. So before, this can vary from, for instance, in Minnesota, just having, requiring one timely stakeholder meeting before the plan is filed, all the way up to having significant upfront input through working groups, as some of the other states require. And then also after the plan is filed, the opportunity for engagement there. So I'm going to talk a little bit more about Hawaii and New York, but I want to point to New Hampshire. They established a stakeholder group, and they really put this group to work. There's real specific recommendations or responsibilities that this group has to make recommendations on things like assumptions and metrics and load and DER forecasting methodologies, as well as hosting capacity, interconnection, and locational value approaches. The image here on this slide is actually a snap from the New York Joint Utilities website. And so I just think it's interesting how kind of clearly laid out everything is here. You can click on hosting capacity, non-wires alternatives. You can go to the filings from the utilities. You can look at a bunch of different things. So this is one approach. Next slide, please. This is a little bit more from the New York process, and so and this was taken from the newsletter, but kind of moving from left to right, they have a whole host of things that they're doing on their stakeholder engagement. They have stakeholder surveys that they send out as a way to try and improve plans from year to year. Then there's the webinars, there's the quarterly newsletters, and then this website that I mentioned, and then company-specific stakeholder meetings. So next slide. As we look at Hawaii, they have the integrated grid planning process. And if you're interested in this subject, really interesting website there with a link to it. But as you look at these four large purple boxes, these are the aspects of the stakeholder engagement process in Hawaii. They have broad public engagement, which includes basically different meetings and virtual open houses where they go to the islands, they meet in high schools or universities, and they try and engage people just in a broad way. There's a stakeholder council that includes representatives from cities and counties and a variety of folks, including the usual participants and dockets, but also reaches into the community. There's working groups, as well as a technical advisory panel of experts from around the country that voluntarily are advising on processes, methodologies, and technologies. Next slide. All right, so getting started, and you can go on to the next slide. We looked around at how are folks getting started with this? There's some good examples to look at of what others have done, and links to everything in case you're interested. But in some cases, staffs have started by developing a report or a white paper outlining what are the key needs, why are they doing this, what are the goals, what's the vision. In a number of states, they've issued surveys to get started, surveys targeting utilities and stakeholders. And then often there'll be some initial meetings to kind of go through those surveys and to really try and understand the current processes, the data that's available, and really the current filings and maybe how they all fit together. Other states have hosted presentations or trainings for the staff and stakeholders. And sometimes this includes taking a look at guidelines that have been developed for other states for distribution system planning. Something interesting that New York did is before they had the utilities file their first plan, they had the utilities file their stakeholder engagement plan. And then they followed that up with an initial distribution system plan and then follow-on plans. And the initial plans sometimes just establish the baseline, just understand the current system, current processes, and then the additional plans can kind of be more forward-looking. So just some ideas there. Next slide. All right, so in emerging issues, and these are going to be my last two slides after this. You can go ahead to the next one. So just a few emerging issues we wanted to touch on with you. One is fire risk, and some of these things can be applied to other risks, maybe in other locations, but in California, they required utilities to develop these wildfire mitigation plans. And if you're interested in this, we've got a lot of extra information, other information in the extra slides, and there's actually just a lot of information in general in the extra slides. So if you're interested in this presentation, it's chock full of information in the back here. But the California wildfire mitigation plans, require the utilities to identify the high-risk zones and how they're going to, handle enhanced inspections, what strategies they're going to use for sectionalizing lines to minimize areas that need to be de-energized, automatic recloser strategies, among other things. So pretty interesting to look at that. Affordability is another emerging issue, and the California PUC's recent decision in affordability docket establishes 3 metrics, and they're listed here. And the New York Public Service Commission has also looked at low-income issues, and in May of 2016 had an order that directed the utility to make filings and adopted a framework for addressing low-income customer needs. Next slide. All right, and so in terms of another emerging issue, and we've heard a little bit about this, but is DER compensation tariffs that are based on locational value. In New York, they have what they call the value stack tariff, and it compensates distributed energy resources based on the location in addition to other things. But as you see, the map here is a Con Edison map where they went through their service territory, the Brooklyn section, and identified areas that they had called location specific relief value zones. And these are zones that can particularly benefit from system relief through distributed energy resources like load relief. So for DERs located in these green areas, in these location-specific relief value zones, they get additional compensation if they're able to provide energy services during call events. So this is another kind of interesting emerging example from New York. All right, so next slide. So we've got lots of resources for you here. Take a look, a lot of great reports and things that you can reference. And then I think the next slide is just the closing. So turn it back over to Carrie.
Thank you so much, Ms. Homer. That was really great. It's really nice hearing all the different things that all the states are doing, and for you to capture it all in one place was just really spectacular. It's one of those on my bucket list, but I'm really glad that you got to it. So thank you so much. Well, thank you for today. I'm going to drop the link to the day 2 evaluations in the chat box for everybody. I will see you tomorrow, and we will send you an email today with the evaluation links. But we will see you tomorrow, same time, same place, 12:30 p.m. Central. Thank you all, and enjoy the rest of your day.